before the oceans existed, before waves traced slow patterns across the surface of the planet, Earth was a very different place. It was not yet the blue world seen from space today, but a young and restless sphere, gradually finding its balance in the vast calm of the early solar system. Time moved differently then, not marked by days and seasons as we know them, but by immense geological rhythms unfolding over millions of years. In this quiet beginning, the foundations for oceans, atmosphere, and life itself were being patiently prepared. Earth formed approximately 4.5 billion years ago from a swirling disk of gas and dust that surrounded the young Sunday. Within this disk, tiny particles collided and adhered, slowly building larger and larger bodies. Over long stretches of time, these collisions gave rise to the rocky planets of the inner solar system. Earth emerged as one of these worlds, shaped by gravity, heat, and constant motion. In its earliest state, the planet was hot, unstable, and largely molten, with a surface dominated by flowing rock rather than solid ground. The heat that defined early Earth came from several sources. Gravitational compression warmed the interior as the planet grew. Frequent impacts from asteroids and planetesimals released enormous energy upon collision. In addition, radioactive elements within Earth's interior decayed and produced heat over time. Together, these processes kept the young planet in a state of near-continuous transformation. The surface was periodically melted and reshaped, erasing features as quickly as they formed. As Earth differentiated, heavier elements such as iron and nickel sank toward the center, forming the core, while lighter silicate materials rose to form the mantle and crust. This separation was slow and persistent, guided by gravity and density rather than sudden events. With differentiation came structure, and with structure came the first hints of long-term stability. Even so, the surface remained inhospitable by modern standards. Exposed to intense radiation from the sun and frequent bombardment from space, above this restless surface, an early atmosphere began to form. Unlike today's oxygen-rich air, this primordial atmosphere was composed primarily of gases released from Earth's interior through volcanic activity. Water vapor, carbon dioxide, nitrogen, methane, and ammonia drifted upward from countless eruptions, accumulating slowly over time. There was little free oxygen, and no protective ozone layer to soften the sun's ultraviolet light. The sky, if one could stand beneath it, would have appeared hazy and unfamiliar. Volcanoes were among the most influential features of this early Earth. They served as steady conduits between the planet's interior and its surface, releasing heat and material in a continuous exchange. Lava flows spread across wide regions, cooling and hardening before being covered again by new layers. Gases escaped alongside molten rock, thickening the atmosphere and contributing essential ingredients for future oceans. Though violent in appearance, volcanism was also a creative force, steadily building the conditions necessary for change. Gradually, as millions of years passed, Earth began to cool. Heat continued to escape into space, radiating away from the surface. As temperatures declined, the outermost layers of the crust spent longer periods in a solid state. Landforms, though still temporary, could persist long enough to influence the movement of air and the accumulation of material. One of the most significant changes during this cooling period involved water, hydrogen, and oxygen, released from volcanic gases and delivered by icy bodies from space, combined to form water vapor in the atmosphere. At first, the intense heat kept this water suspended as gas, but as surface temperatures fell below critical thresholds, condensation began. Clouds formed, thick and heavy, drifting above a world that had never known rain. When precipitation finally began, it did not fall gently at first. Rain likely continued for extended periods, possibly thousands of years, pouring steadily onto the hot surface. As droplets met warm rock, much of the water evaporated again, returning to the sky. This cycle repeated endlessly, a slow negotiation between heat and cooling, between sky and stone. Over time, as the surface cooled further, more water remained in liquid form, collecting in low-lying areas. These earliest pools of liquid water were transient, forming and disappearing as conditions shifted. Yet each cycle allowed water to interact with minerals in the crust, dissolving elements and transporting them across the surface. In this way, water began its long role as a planetary mediator, reshaping landscapes not through force, but through persistence. Even before oceans existed, water was quietly at work. During this era, Earth had no life in any recognizable form. There were no organisms, no cells, no metabolism. And yet, the planet was far from static. Chemical reactions unfolded constantly, driven by heat, radiation, and the movement of matter. Simple molecules formed and broke apart in the atmosphere and on the surface, participating in countless interactions. Though lifeless, Earth was becoming chemically complex, laying groundwork that would later prove essential. The absence of oxygen in the atmosphere played a crucial role in these early conditions. Without oxygen to rapidly break down organic molecules, certain compounds could persist longer than they would today. This allowed carbon-based molecules to accumulate in small amounts. These molecules did not yet constitute life, but they represented an increase in chemical richness, a subtle shift toward complexity. Time, during this phase of Earth's history, stretched beyond ordinary comprehension. Events that seemed dramatic, when compressed into sentences, unfolded gradually, almost imperceptibly. Cooling by a few degrees could take millions of years. The settling of a crust, the thinning of an atmosphere, the accumulation of water, all progressed at a pace that allowed the planet to adjust and respond. Nothing was hurried, and nothing was wasted. As Earth continued to cool, the conditions necessary for stable bodies of water drew closer. The balance between incoming solar energy and outgoing heat shifted. The surface spent more time below the boiling point of water. Rainfall began to exceed evaporation, and liquid water could persist for longer intervals. Basins deepened, channels formed, and the earliest outlines of seas began to emerge. This was the quiet threshold before the oceans, a moment defined not by sudden transformation, but by readiness. Earth had not yet become a living planet, but it was no longer a purely molten world. It existed in a state of transition, poised between fire and water, between chaos and order. The stage was nearly set, and the slow arrival of the oceans would soon change everything, not through force, but through calm and enduring presence. In this stillness, before waves and tides, before organisms and ecosystems, Earth was learning how to be stable. It was practicing patience, allowing physical laws to guide its evolution, and in doing so, it prepared a vast and gentle environment where, much later, the first forms of life would quietly appear. 2. The arrival of water on a cooling planet. As Earth continued its long, gradual cooling, one of the most transformative substances in its history began to take on a more permanent role. Water, which had existed largely as vapor in the early atmosphere, slowly transitioned into a liquid that could remain on the surface. This change did not happen all at once, nor did it follow a simple path. Instead, it unfolded through countless cycles of evaporation and condensation. In the earliest stages, water molecules were released primarily from Earth's interior. Volcanic activity, which remained widespread across the planet, expelled enormous quantities of steam, along with other gases. Each eruption added more water vapor to the atmosphere, thickening it and increasing its capacity to hold heat. This dense, moisture-laden air played a dual role, trapping warmth near the surface, while also providing the raw material for future rainfall. The planet, still warm but steadily cooling, Beyond volcanic sources, additional water likely arrived from space. Icy bodies, such as comets and water-rich asteroids, collided with Earth during its formative years. When these objects struck the surface, much of their ice was vaporized by the heat of impact, releasing water into the atmosphere. Though each collision was brief, their cumulative effect over millions of years was substantial. Together with volcanic outgassing, these deliveries helped ensure that water became one of the most abundant compounds on the planet. As surface temperatures declined, clouds formed more readily and persisted longer. Thick layers of condensed water vapor drifted across the sky, obscuring sunlight and softening temperature extremes. Eventually, rain began to fall in earnest. These early rains may have lasted for extraordinary lengths of time, perhaps falling almost continuously for centuries or longer. The sound and sensation of such rainfall, if it could be experienced, would have been steady and unbroken, shaping the surface grain by grain. When rain reached the ground, it encountered a landscape still dominated by rock and newly solidified crust. In many places, the surface remained hot enough to cause immediate evaporation, sending water back into the atmosphere. Elsewhere, where temperatures had cooled sufficiently, water pooled briefly before flowing away or soaking into cracks. Each interaction between water and rock altered both, dissolving minerals, widening fractures, and smoothing rough edges. These interactions marked the beginning of erosion, a slow but powerful force. Water is uniquely suited to movement. Guided by gravity, it seeks the lowest points, flowing along the surface and through the crust. Over time, repeated rainfall carved shallow channels, directing water toward basins and depressions. These low-lying areas became natural collection points, allowing liquid water to persist longer than elsewhere. For the first time, water was staying put. The atmosphere continued to evolve alongside these surface changes. As rain removed water vapor from the air, pressure and composition gradually shifted. Carbon dioxide, another abundant volcanic gas, dissolved readily into falling rain and collected waters. This process reduced the greenhouse effect slightly, contributing to further cooling. In this way, water actively shaped the climate, participating in feedback loops that reinforced its own stability. With each cycle of rainfall and collection, the surface of Earth became more varied. Some regions remained dry and elevated, while others grew increasingly wet. Mineral-rich water flowed across basaltic rock, carrying dissolved elements into basins. Salts, metals, and other compounds accumulated slowly, creating chemically diverse environments. These dissolved substances would later play a crucial role in biological processes. But for now, they simply enriched the water itself. At this stage, Earth still lacked oceans in the modern sense. Instead, it hosted countless lakes, seas, and shallow basins that expanded and contracted with changing conditions. Some dried out and refilled repeatedly, while others deepened over time as erosion lowered surrounding land. The persistence of these water bodies depended on local temperature, geography, and the balance between rainfall and evaporation. Stability emerged unevenly, patch by patch. The role of gravity cannot be overstated in this process. As Earth's mass pulled water downward, it ensured that liquid water would always collect in the lowest available spaces. Over geological timescales, this tendency led to the merging of separate basins. Channels widened, boundaries eroded, and waters slowly connected. What began as isolated pools gradually formed networks, setting the stage for the first expansive seas. Beneath the surface, water also began to penetrate the crust. It seeped into fractures and pores, interacting with hot rock below. In these hidden environments, water was heated and circulated, emerging again through vents and fissures. This circulation redistributed heat and chemicals, linking surface and subsurface systems. Even before life existed, Earth was developing internal pathways that would later become essential habitats. Throughout this period, The sun continued to provide energy, though it was slightly dimmer than it is today. Despite this reduced output, the thick atmosphere helped retain enough warmth for liquid water to persist. The balance between solar input and atmospheric insulation was delicate. A small shift in either direction could have led to a frozen world or a perpetually steaming one. Instead, Earth remained within a narrow window that favored liquid water. As water accumulated, its presence transformed the planet's appearance. The surface grew darker where wet rock absorbed light. Reflections appeared for the first time as pools mirrored the sky above. Movement became more fluid, with streams flowing and merging in slow, predictable patterns. The planet was learning new rhythms, guided by cycles of precipitation and flow. These early waters were not clear or tranquil by modern standards. They were warm, mineral-rich, and often turbulent, stirred by ongoing volcanic activity and meteor impacts. Yet within their constant motion lay a remarkable consistency. Water flowed, collected, and persisted, following physical laws with unwavering reliability. This predictability would later allow chemical systems to repeat, refine, and stabilize. Importantly, water also served as a solvent, bringing molecules together and allowing them to interact more freely. In liquid form, substances could dissolve, diffuse, and react in ways not possible in dry or gaseous environments. Though life had not yet emerged, the conditions that would eventually support it were quietly assembling within these waters. Over immense spans of time, as rainfall continued and basins deepened, Earth moved closer to a global transformation. Individual bodies of water expanded and merged, their boundaries blurring. The concept of a single, connected ocean was still far in the future, but its foundations were being laid. Each drop of water that fell and remained contributed to this unfolding story. By the end of this phase, water was no longer a fleeting visitor to Earth's surface. It had become a defining feature, shaping climate, geology, and chemistry alike. The planet had crossed an important threshold, entering an era where liquid water could endure. With this stability came new possibilities and the quiet preparation for the next chapter in Earth's long and patient history. 3. The formation of the first global oceans. Over long spans of time, as rainfall continued and surface temperatures stabilized, Earth's scattered bodies of water began to change in character. What had once been isolated pools and transient seas slowly deepened and expanded, guided by gravity and erosion. The planet's surface, no longer dominated solely by molten rock, now bore wide depressions capable of holding vast quantities of liquid water. These regions became the quiet gathering places where the first true oceans would eventually take shape. The cooling of Earth played a central role in this transformation. As heat steadily escaped into space, the surface remained below the boiling point of water for longer and longer intervals. Evaporation still occurred, but it no longer erased every trace of rainfall. Instead, a balance emerged between water entering the surface through precipitation and water returning to the atmosphere. This balance allowed liquid water to persist across much of the planet, marking a decisive shift in Earth's physical state. Gravity ensured that water flowed toward the lowest elevations, and over millions of years these lowlands expanded. Repeated rainfall and surface runoff wore down higher terrain, carrying sediments into basins and smoothing the landscape. The process was slow and unrelenting, with each droplet contributing to the gradual reshaping of the crust. Valleys widened, channels deepened, and separate basins inched closer together until water could move freely between them. As connections formed, individual bodies of water merged into larger systems. Streams fed lakes, lakes overflowed into neighboring depressions, and shallow seas spread outward. What had once been a patchwork of isolated waters began to resemble a network with increasing continuity across the surface. The boundaries between land and water shifted repeatedly, but the overall trend favored expansion. Water was becoming the dominant feature of the planet's exterior. These early oceans were likely warm by modern standards, heated by both the sun and Earth's interior. Geothermal energy continued to seep upward through the crust, especially along fractures and volcanic regions beneath the water. This heat created gradients within the oceans, with warmer waters rising and cooler waters sinking, establishing slow circulation patterns. Even at this early stage, the oceans were dynamic, constantly moving and mixing. The chemistry of these growing oceans reflected their origins. Rainwater carried dissolved gases from the atmosphere, including carbon dioxide, nitrogen, and trace compounds. As water flowed over rock, it leached minerals such as iron, magnesium, calcium, and silica from the crust. These substances accumulated gradually, giving the oceans a composition far different from today's seawater. Salinity levels were likely lower at first, increasing over time as minerals continued to dissolve and concentrate. As oceans expanded, they began to exert a stabilizing influence on Earth's climate. Water has a high capacity to absorb and store heat, which allowed the oceans to moderate temperature fluctuations. During warmer periods, excess heat was absorbed, and during cooler intervals, stored heat was released. This buffering effect reduced extremes and promoted greater overall stability, reinforcing the persistence of liquid water on the surface. The presence of large bodies of water also altered atmospheric circulation. Evaporation from ocean surfaces added moisture to the air, contributing to cloud formation and precipitation elsewhere. Winds carried this moisture across the planet, redistributing water and energy. In this way, oceans and atmosphere became linked in an ongoing exchange, each influencing the other in subtle but significant ways. At this point in Earth's history, the continents as we know them did not yet exist. Instead, the crust was divided into smaller, shifting landmasses surrounded by water. Tectonic activity remained vigorous, with plates forming, moving, and recycling crustal material. New seafloor was created at volcanic ridges beneath the oceans, while older sections were altered or consumed elsewhere. The oceans were not static containers but active participants in planetary change. Beneath the surface, the interaction between water and rock continued to intensify. Seawater penetrated deep into the crust through fractures, where it was heated and chemically altered before returning to the ocean through vents. These processes enriched the water with additional minerals and created localized environments with distinct chemical conditions. Though life had not yet appeared, the oceans were already developing a diversity of settings. Light from the sun penetrated the upper layers of these early oceans, illuminating vast expanses of water. Below, darkness prevailed, punctuated by the glow of geothermal activity in certain regions. This vertical structure introduced variation, with conditions differing dramatically from surface to depth. Such variation would later prove essential for biological diversity, but even now, it contributed to chemical complexity. The sheer scale of the oceans marked a turning point in Earth's story. Water now covered a significant portion of the planet's surface, forming a continuous envelope that connected distant regions. This connectivity allowed materials and energy to move freely across the globe, linking systems that had once been separate. Earth had become a truly oceanic world. Time continued its steady passage, and with it the oceans grew deeper and more stable. Shorelines shifted gradually, responding to tectonic movement and changes in water volume. Sediments settled onto the seafloor, forming layered records of environmental conditions. Each layer captured a moment in time, preserving subtle clues about temperature, chemistry, and geological activity. The oceans also acted as repositories, collecting and retaining substances over immense periods. Gases dissolved in seawater, minerals accumulated, and chemical reactions unfolded continuously. Unlike the atmosphere, which could change relatively quickly, the oceans evolved more slowly, integrating changes over long durations. This inertia added another layer of stability to the planet's systems. Although the oceans were lifeless in a biological sense, they were far from inactive. Chemical reactions occurred constantly, driven by energy from sunlight, heat, and electrical discharges in the atmosphere. Molecules collided, bonded, and separated in endless combinations. The oceans provided a medium where these processes could occur repeatedly, increasing the likelihood of complex outcomes. As Earth settled into this ocean-dominated state, the conditions necessary for further transformation quietly assembled. The planet now possessed vast, stable bodies of liquid water, a chemically rich environment, and a range of energy sources. These factors did not guarantee the emergence of life, but they made it possible. The oceans had become more than collections of water. They were integrated systems shaping the future of the planet. In this era of deep time, nothing announced the significance of these changes. There were no sudden markers, no clear boundaries between before and after. Instead, the formation of the first global oceans unfolded as a smooth continuation of Earth's cooling and stabilization. Water flowed, collected, and endured, and in doing so, it prepared the quiet stage upon which the next great chapter of Earth's history would eventually begin. 4. The chemistry of ancient seawater. As the first global oceans settled into place, they became more than vast reservoirs of water. They turned into active chemical systems, constantly shaped by interactions between water, rock, atmosphere. The ancient seas were not clear or chemically simple. Instead, they were dense with dissolved substances, quietly accumulating complexity as time moved forward at its unhurried pace. Rainfall continued to deliver gases from the atmosphere into the oceans. Carbon dioxide dissolved readily in seawater, forming weak acids that gently altered the chemistry of the oceans and the rocks they touched. Nitrogen compounds, sulfur-bearing gases, and trace elements also entered the water, contributing to a mixture that was constantly evolving. Each rainfall subtly adjusted the balance, and over millions of years these small changes added up. The seafloor itself was a major source of chemical enrichment. Newly formed oceanic crust, rich in basalt, interacted directly with seawater. Water seeped into cracks and fissures, was heated by the underlying mantle, and then rose again carrying dissolved minerals. Iron, magnesium, calcium, and silica entered the oceans through these processes. The oceans were not passive recipients. They actively extracted substances from the planet beneath them. Volcanic activity beneath the oceans added another layer of chemical input. Submarine volcanoes released gases directly into the water, including hydrogen sulfide, methane, and carbon dioxide. These compounds altered local chemistry and created regions of strong chemical gradients. Even far from volcanic centers, the influence of these inputs spread slowly through ocean circulation, ensuring that no part of the ocean was entirely isolated from the planet's interior. The temperature of ancient seawater played a crucial role in its chemistry. Warmer water can hold different concentrations of dissolved gases and minerals than cooler water. In the early oceans, elevated temperatures allowed for higher reaction rates, enabling chemical processes to proceed more rapidly than they would today. Molecules collided more frequently. Bonds formed and broke with ease, and equilibrium states shifted continuously. Salinity in these early oceans was likely lower than in modern seas, at least initially. Sodium and chloride ions accumulated slowly, changing the electrical properties of seawater and influencing how other molecules behaved. This gradual rise in salinity was another example of how the oceans evolved, not through sudden events, but through steady accumulation. Iron played an especially prominent role in ancient seawater chemistry. With little oxygen present in the atmosphere or oceans, iron remained in soluble forms, dispersing widely through the water. This gave parts of the ancient oceans a distinct chemical character, very different from today's iron-poor seas. Iron participated in numerous chemical reactions, acting as a catalyst and energy mediator in processes that would later become biologically important. The absence of oxygen shaped nearly every aspect of ocean chemistry during this time. Without oxygen to react with and remove many compounds, these substances created an environment rich in chemical potential. where reactions could proceed along pathways no longer common on modern Earth. The oceans were chemically alive, even though biological life had not yet emerged. Sunlight interacted with the surface waters, providing energy that drove additional reactions. Ultraviolet radiation, unfiltered by an ozone layer, penetrated the upper layers of the ocean. While intense, this radiation also supplied energy that altered molecular structures and encouraged new combinations. Near the surface, chemistry was influenced by light. Deeper down, it was shaped more by heat and pressure. This vertical variation added another dimension to the ocean's chemical landscape. Water itself acted as a stabilizing medium. Its ability to dissolve a wide range of substances allowed different compounds to coexist and interact. Molecules that might never meet in a dry environment could encounter one another in solution. This constant mixing, driven by currents and diffusion, ensured that chemical processes were not confined to isolated pockets. The movement of ocean water played a key role in distributing chemicals. Even in these early oceans, temperature differences and salinity variations drove slow circulation patterns. Warm, less dense water rose while cooler, denser water sank, setting up gentle currents. These motions blended chemical inputs from different sources, smoothing extremes and creating more uniform conditions across vast distances. At the same time, localized environments retained distinct chemical identities. Shallow coastal regions differed from deeper basins, and areas near volcanic activity differed from quieter seafloor plains. These variations meant that the oceans were not chemically uniform. Instead, they contained a mosaic of environments, each with its own balance of substances and reactions. This diversity increased the range of possible chemical pathways available. Over immense spans of time, sediments settled on the ocean floor, carrying with them chemical signatures of the water above. These sediments locked away certain compounds, altering the composition of the remaining seawater. Meanwhile, new material continued to enter the system from volcanic and tectonic processes. The oceans thus operated as both sinks and sources, constantly adjusting their chemical makeup. The interaction between seawater and the atmosphere remained ongoing. Gases dissolved into the oceans and were later released back into the air through evaporation and volcanic outgassing. This exchange linked the chemistry of sea and sky, allowing changes in one to influence the other. Carbon cycles, though entirely abiotic at this stage, were already in motion, circulating elements between different parts of the planet. As chemical complexity increased, the oceans became increasingly capable of supporting intricate reactions. Organic molecules, formed through non-biological processes, could persist and accumulate under certain conditions. These molecules did not yet constitute life, but they represented steps along a continuum from simple chemistry toward greater organization. The oceans provided both the space and the stability needed for such progression. Throughout this period, the pace of change remained slow and deliberate. Chemical systems evolved gradually, guided by physical laws rather than chance alone. Reactions that proved stable under prevailing conditions persisted, while others faded away. This quiet selection, driven by energy flows and environmental constraints, shaped the chemical character of the oceans long before biological evolution began. By the end of this phase, Earth's oceans were chemically rich, dynamic, and deeply integrated into the planet's systems. They had become more than collections of water and dissolved minerals. They were active environments where complexity could arise and endure. The ancient seas, in their calm persistence, had prepared a chemical foundation upon which the first organisms would eventually find a home, continuing the slow and patient unfolding of Earth's story. 5 energy sources in a sunlit and volcanic world. As Earth's early oceans deepened and spread across the planet, they became the setting for a continuous exchange of energy. Nothing within these waters existed in stillness. Heat moved, light filtered downward, and chemical gradients formed and dissolved again. Long before life appeared, energy was already flowing through the system. The most constant source of energy reaching the oceans was the sunday. Though slightly dimmer than it is today, the young sun still delivered a steady stream of radiation to Earth's surface. Sunlight struck the upper layers of the oceans, warming the water and driving evaporation. This energy input established daily and seasonal rhythms, even in a world without biological clocks. Light did not penetrate deeply, but where it reached, it altered temperature and chemistry in subtle but persistent ways. In the absence of an ozone layer, ultraviolet radiation reached the ocean surface more readily than it does today. While intense, this radiation did not simply act as a destructive force. It also supplied energy capable of breaking molecular bonds and allowing new ones to form. Near the surface, sunlight energized chemical reactions, creating a dynamic zone where molecules were constantly reshaped. This photochemical activity added complexity to the ocean's upper layers, even in the absence of life. Beneath the reach of sunlight, another source of energy made itself known. Earth's interior remained warm, and heat flowed steadily outward through the crust. In places where the seafloor was thin or fractured, this heat escaped more easily, warming the surrounding water. The result was a vertical gradient, with warmer waters rising and cooler waters sinking, creating slow but persistent circulation. This movement distributed energy throughout the oceans, ensuring that heat did not remain confined to isolated regions. Volcanic activity beneath the oceans contributed additional energy in concentrated bursts. Submarine eruptions released heat directly into the surrounding water, sometimes creating localized plumes of warmth that rose toward the surface. Along with heat, these eruptions released chemically reactive substances, adding another layer of energetic potential. Though these events were episodic, their influence lingered as altered chemistry and temperature spread outward over time. Hydrothermal systems emerged where seawater interacted with hot rock below the seafloor. Water percolated downward through cracks, was heated by the mantle, and then returned to the ocean, enriched with dissolved minerals. This process created environments where temperature and chemistry differed sharply from the surrounding water. These gradients represented stored energy, capable of driving chemical reactions as substances moved from high energy to lower energy states. Chemical energy played a particularly important role in this early world. Differences in concentration between substances created gradients that naturally tended toward balance. When molecules moved down these gradients, energy was released. In the ancient oceans, such gradients were common, especially near volcanic regions and hydrothermal systems. Hydrogen-rich fluids mixed with carbon-bearing compounds, sulfur compounds interacted with metals, and reactions unfolded without biological guidance. The oceans thus became layered with different energy regimes. At the surface, sunlight dominated, driving thermal cycles and photochemical reactions. In the depths, geothermal heat and chemical gradients shaped the environment. Between these extremes lay vast volumes of water, where energy moved more slowly, carried by currents and diffusion. This stratification introduced variety, allowing multiple processes to occur simultaneously across different regions. The movement of energy was closely tied to the movement of matter. Warm water rose, carrying dissolved substances upward, while cooler water sank, transporting materials downward. This circulation ensured that no part of the ocean remained completely isolated. Even regions far from volcanic activity or direct sunlight eventually felt their influence through slow mixing. Over long timescales, energy and matter became thoroughly intertwined. Electrical energy also played a role, though less visibly. Lightning storms in the early atmosphere discharged energy into the oceans, particularly in shallow regions. These electrical pulses provided brief but intense energy inputs, capable of driving chemical reactions that might not occur otherwise. Though fleeting, such events added another dimension to the energetic landscape of early Earth. The combination of energy sources created an environment rich in possibility. Heat, light, and chemical gradients coexisted, overlapping in space and time. No single source dominated entirely. Instead, their interplay shaped a complex and ever-changing system. This diversity of energy inputs increased the range of chemical processes that could occur, allowing molecules to explore many different configurations. Importantly, energy flowed continuously. There were no long pauses, no extended periods of complete equilibrium. Even when conditions appeared stable on the surface, energy was moving beneath, around, and through the oceans. This constant flow prevented chemical systems from stagnating. Reactions could proceed, reverse, and proceed again, refining patterns through repetition rather than sudden change. Over immense spans of time, certain reactions proved more persistent than others. Those that could be sustained by the available energy sources continued, while others faded away. This process was not directed, but it was not random either. Physical laws favored reactions that efficiently dissipated energy, allowing systems to settle into stable pathways. In this sense, energy acted as a quiet guide, shaping complexity long before life appeared. The oceans, warmed from above and below, became vast reservoirs of stored energy. They absorbed heat during warmer periods and released it during cooler ones, smoothing transitions and promoting long-term stability. This buffering effect protected the chemical systems within, allowing them to persist across changing conditions. Stability, once achieved, became self-reinforcing. As energy flowed through the oceans, it fostered increasingly intricate chemical interactions. Molecules encountered one another repeatedly, driven together by currents and gradients. Bonds formed, broke. While none of this constituted life, it represented a gradual increase in organization, made possible by the steady availability of energy. By this stage in Earth's history, the planet possessed all the major forms of energy that would later support living systems. Sunlight illuminated the surface, geothermal heat warmed the depths, and chemical gradients stored potential energy throughout the oceans. These forces operated quietly and persistently, requiring no direction and no intention. The ancient oceans thus became not only chemical reservoirs, but energetic ones as well. They gathered, stored, and redistributed energy across the planet, creating a stable yet dynamic environment. Within this environment, complexity could arise slowly and endure. The flow of energy, gentle and unbroken, carried Earth one step closer to a world where the first organisms would eventually find the conditions they needed to exist. 6. Simple molecules in endless motion. Within the ancient oceans, long before cells or organisms existed, the water was filled with motion too small to be seen yet constant and unceasing. Molecules drifted, collided, separated, and recombined in patterns guided by temperature, chemistry, and chance. There was no intention in this movement, no direction toward life, and yet the conditions allowed complexity to quietly increase through repetition and time. Water itself was the primary medium for this molecular motion. Each molecule of water moved freely, slipping past others, forming and breaking weak bonds as temperature and pressure shifted. This fluidity allowed dissolved substances to travel, ensuring that no molecule remained isolated for long. Carbon-based compounds, simple gases, and mineral ions were carried along in this slow, endless circulation. Carbon played a central role in this early chemical world. Released from volcanic gases and dissolved from rocks, carbon atoms combined readily with hydrogen, oxygen, and nitrogen. These combinations formed simple organic molecules, including small hydrocarbons and carbon-containing acids. None of these substances were alive, yet they possessed structures capable of variation, stability, and interaction. In the vastness of the oceans, such molecules existed in enormous numbers, each participating in countless encounters. Movement ensured opportunity. Thermal energy caused molecules to vibrate and drift, while currents carried them across distances great and small. Near the surface, sunlight added energy, increasing molecular motion and encouraging reactions. Even in regions far from obvious energy sources, diffusion ensured that molecules continued to explore their surroundings. Most molecular encounters were brief and unremarkable. Two molecules might collide and drift apart unchanged, or they might briefly bond only to separate again moments later. Yet over immense spans of time, even rare events occurred often enough to matter. A bond that formed once in a million collisions would eventually form countless times across the global oceans. Time, more than chance, was the key factor. Certain environments enhanced these interactions. Shallow waters, where evaporation concentrated dissolved substances, brought molecules closer together. Mineral surfaces provided places where molecules could adhere temporarily, increasing the likelihood of reaction. Porous rocks and sediments trapped compounds in small spaces, allowing repeated interactions within confined volumes. These settings did not create life, but they made chemical exploration more efficient. Simple organic molecules exhibited a range of behaviors. Some were relatively stable, persisting in seawater for long periods. Others were reactive, readily forming new compounds under the right conditions. Energy inputs from light, heat, or chemical gradients could push reactions forward, while cooling or dilution might reverse them. The oceans thus hosted a constantly shifting balance between formation and breakdown. Water's role as a solvent was crucial. By surrounding molecules and stabilizing charged regions, water allowed reactions to proceed that would be impossible in dry environments. It cushioned collisions, moderated temperature changes, and enabled gradual transitions rather than abrupt disruptions. In this way, water acted as both participant and moderator, supporting complexity without enforcing it. As molecules moved and interacted, patterns began to emerge. Certain reactions occurred more readily than others, producing compounds that persisted longer or interacted more effectively with their surroundings. These molecules became more common not through selection, but through stability. Those that broke down quickly simply did not accumulate, while those that endured became part of the ocean's background chemistry. Some molecules began to associate loosely, forming clusters held together by weak forces. These assemblies were temporary, forming and dissolving repeatedly. Yet even such fleeting structures mattered, as they demonstrated that molecules could organize themselves under the right conditions. Organization did not require life. It required only suitable chemistry and sufficient time. The motion of molecules was not uniform throughout the oceans. Temperature gradients created regions of faster and slower movement. In warmer areas, molecules collided more frequently, increasing reaction rates. In cooler regions, reactions slowed, allowing certain compounds to persist longer. This variation added depth to the chemical landscape, ensuring that different processes could dominate in different places. Electrical charges also influenced molecular behavior. Ions dissolved in seawater created local electrical environments that attracted or repelled other molecules. These interactions affected how compounds aligned, bonded, and moved. Minerals dissolved from the crust contributed to this complexity, introducing charged species that altered reaction pathways. Despite this complexity, the system remained gentle. There were no sudden leaps, no dramatic transformations. Changes accumulated slowly, almost imperceptibly. Molecules explored possibilities through endless repetition, guided by physical laws rather than direction. The oceans served as a vast testing ground, where chemistry unfolded patiently. Importantly, breakdown was as common as formation. Molecules that formed under one set of conditions could be dismantled under another. Sunlight might break bonds near the surface, while heat might rearrange structures at depth. This constant recycling prevented stagnation and ensured that chemical systems remained dynamic. Over millions of years, this steady motion increased the diversity of compounds present in the oceans. New molecules appeared, some fleeting, others more enduring. The overall chemical inventory grew richer, even though no single molecule or process dominated. Complexity arose not from accumulation alone, but from interaction. The absence of life meant there was no consumption or purposeful use of these molecules. Without organisms to disrupt or redirect processes, chemical systems could explore configurations freely, governed only by energy availability and environmental constraints. In this world of endless motion, repetition was essential. A single reaction might mean nothing, but billions of repetitions over vast spans of time created familiarity. Molecules encountered the same conditions again and again, allowing stable patterns to persist. This persistence laid the groundwork for future developments, even though those developments were not yet inevitable. As Earth continued to evolve, the oceans maintained their role as arenas of motion and interaction. Molecules drifted through sunlit waters and shadowed depths, carried by currents and stirred by heat. Each movement was small, each interaction fleeting, yet together they formed a continuous process that never truly paused. By the end of this stage, the oceans were alive with chemistry, though still devoid of biology. Simple molecules moved endlessly, forming and dissolving in quiet cycles. In their motion lay potential, not yet realized, but steadily preserved by the stability of water, energy, and time. The stage was becoming more prepared, even if no one could yet recognize what would one day emerge. 7 natural patterns in self-organization. Within the ancient oceans, as simple molecules continued their endless motion, certain patterns began to appear. These patterns were not imposed from above, nor were they guided by intention. They emerged naturally from the interaction of matter and energy, shaped by physical laws that favored order under the right conditions. This quiet phenomenon, known as self-organization, unfolded slowly and subtly, yet it carried profound significance for the future of Earth. Self-organization occurs when components of a system arrange themselves into structured patterns without external direction. In the early oceans, the ingredients for such behavior were abundant. Molecules existed in vast numbers. Energy flowed continuously, and the environment provided stability over immense periods of time. Under these circumstances, it was inevitable that certain arrangements would arise more often than others, simply because they were more stable. Temperature gradients played a key role in this process. Where warm water met cooler regions, motion increased and patterns of flow developed. These currents were not random. They followed predictable paths shaped by density differences and gravity. Within these moving waters, molecules were carried together repeatedly, increasing the likelihood of interaction. Over time, this repetition reinforced certain spatial arrangements. Chemical gradients also contributed to emerging order. Differences in concentration between substances created zones where reactions were more likely to occur. As molecules moved from areas of high concentration to lower concentration, energy was released, and reactions followed favored pathways. These pathways, once established, tended to persist as long as the gradients remained. Thus, structure emerged not as a fixed form, but as a dynamic process sustained by flow. Mineral surfaces provided additional opportunities for organization. When molecules encountered rock or sediment, they could adhere temporarily, aligning themselves in ways not possible in open water. These surfaces acted as gentle scaffolds, allowing molecules to remain in close proximity long enough for interactions to occur. Over countless repetitions, such interactions could favor certain configurations over others. In shallow regions where water periodically evaporated and returned, cycles of concentration and dilution occurred. As water evaporated, dissolved substances were drawn closer together, increasing the likelihood of bonding. When water returned, some of these bonds persisted, while others broke apart. These cycles acted as natural experiments, testing which molecular arrangements could endure changing conditions. Self-organization was not limited to chemistry alone. Physical patterns also emerged within the oceans. Convection currents formed as warm water rose and cooler water sank. These currents created repeating loops of motion, distributing heat and substances in predictable ways, even without life. The oceans exhibited a kind of rhythm, driven by energy flow and constrained by physical boundaries. One of the remarkable aspects of self-organization is that it does not require complexity to begin. Simple rules applied repeatedly can produce structured outcomes. In the early oceans, the rules were provided by physics and chemistry. Molecules moved according to energy gradients, bonded according to their properties, and separated when conditions changed. From these simple behaviors, larger patterns gradually arose. Certain chemical systems demonstrated an ability to persist by cycling through reactions. These cycles did not represent life, but they showed that chemistry could sustain organized behavior over time. Stability did not mean stillness. It meant reliable repetition. Energy flow was essential for maintaining these patterns. Without a constant input of energy, systems would drift toward equilibrium, where no net change occurred. The early oceans avoided this fate because energy was always present, supplied by sunlight, geothermal heat, and chemical gradients. This continuous input kept systems away from equilibrium, allowing patterns to persist and evolve. Importantly, self-organization favored efficiency. Arrangements that dissipated energy effectively were more likely to endure. This principle guided the emergence of stable patterns without requiring selection or competition. Systems that could maintain structure while accommodating energy flow simply lasted longer than those that could not. Over time, the oceans became filled with overlapping patterns of organization. None dominated entirely, and none were permanent. They appeared, shifted, and sometimes vanished as conditions changed. Yet the overall tendency toward structure remained. Order emerged not in opposition to disorder, but alongside it, woven into the movement of water and molecules. These processes unfolded over spans of time so vast that change was nearly imperceptible. Millions of years might pass with only subtle adjustments in pattern and behavior, yet patience was rewarded. Each small refinement added to the ocean's capacity to support complexity. The environment became increasingly rich in organized chemical activity. Even though no living systems yet existed, the absence of life allowed these processes to proceed without interference. There were no organisms to consume resources, alter gradients, or impose biological constraints. Chemistry explored its possibilities freely, guided solely by environmental conditions. This freedom allowed self-organizing systems to develop naturally and persist long enough to matter. Self-organization also introduced memory into the system, not memory in a conscious sense, but persistence. Patterns that endured carried forward information about the conditions that supported them. When similar conditions arose again, similar patterns reappeared more readily. In this way, the oceans developed a kind of chemical familiarity, shaped by past interactions. As Earth continued to cool and stabilize, the range of conditions supporting self-organization expanded. More environments became hospitable to structured chemistry. Shallow seas, deep basins, and mineral-rich vents each contributed their own variations. The oceans became a mosaic of organized processes, quietly increasing the planet's potential. None of these developments guaranteed the emergence of life. Self-organization alone is not life, just as structure is not purpose. Yet without self-organization, life as we know it could not arise. The ability of matter to arrange itself into stable, repeating patterns was a necessary foundation, patiently established long before biology entered the scene. By the end of this stage, Earth's oceans were no longer just chemically complex, they were structurally dynamic. Patterns of flow, reaction, and organization existed across scales. From microscopic interactions to global circulation, these patterns did not announce themselves, nor did they strive toward a goal. They simply persisted. In this quiet persistence lay promise. The oceans had learned how to organize themselves, how to sustain structure without design. As conditions continued to evolve, this capacity would prove essential. The groundwork had been laid gently and thoroughly, ensuring that when the first true biological systems finally appeared, they would find an environment already practiced in the art of order. 8 sheltered environments, tidal pools and seafloors. As Earth's oceans matured and spread across the planet, not all regions within them were alike. Beyond the open waters, where currents moved freely and conditions shifted gradually, there existed quieter, more protected environments. These sheltered places, found along early coastlines, shallow basins, and the ocean floor itself. In these regions, water lingered, chemistry concentrated, and time worked with particular patience. Along the edges of ancient seas, shallow waters collected in natural depressions. These early tidal pools formed where the land met the ocean, shaped by uneven rock surfaces and gentle changes in sea level. Water flowed in and out of these pools as conditions allowed, sometimes replenished by rainfall, sometimes refreshed by the sea itself. Though simple in appearance, these pools experienced cycles unlike those of the open ocean. In shallow waters, evaporation played a more prominent role. Sunlight warmed the surface, encouraging water to escape into the air while leaving dissolved substances behind. As a result, molecules became more concentrated, increasing the likelihood of interaction. When water returned, either through rain or renewed contact with the sea, some of the chemical products remained. This repeating cycle of concentration and dilution created a slow rhythm, allowing chemistry to experiment gently and persistently. These coastal environments were also rich in mineral surfaces. Rocks exposed to water provided places where molecules could settle temporarily, aligning and interacting in ways not possible in free solution. Cracks and crevices trapped water, protecting it from immediate mixing with the surrounding ocean. Within these small spaces, conditions could remain stable for extended periods, offering chemistry a kind of quiet refuge. Below the surface, the ocean floor offered another form of shelter. Vast expanses of seafloor lay far from the turbulence of surface waters, insulated from rapid temperature changes and intense radiation. Here, sediments accumulated slowly, forming layers that recorded the history of the oceans above. Water moving through these sediments encountered a complex landscape of pores and channels, each shaping chemical interactions in subtle ways. The seafloor was not uniform. Some regions were smooth plains, while others were marked by ridges, vents, and fractured rock. In places where tectonic activity was present, heat from below warmed the surrounding water. This variation created a range of environments, each offering different balances of temperature, chemistry, and movement. Water circulating through the seafloor interacted continuously with rock. As it moved, it dissolved minerals and altered both itself and the material it passed through. This process enriched the water with chemical components while also transforming the crust. Over time, these interactions created localized environments where chemistry differed noticeably from that of the open ocean. Sheltered environments also moderated the movement of water itself. In tidal pools and sediment-filled regions, water flowed more slowly, reducing the dispersal of molecules. This reduced motion allowed compounds to remain close together for longer periods, increasing the chance of sustained interaction. Stability, rather than speed, became the defining feature of these places. Light reached shallow waters more easily than it did the depths, introducing another dimension of variation. In sunlit pools, energy from light influenced chemical reactions directly. In contrast, deeper sheltered environments relied more on heat and chemical gradients. Together, these settings provided complementary conditions, expanding the range of possible processes occurring across the planet. The importance of these environments lay not in dramatic change, but in persistence. While open ocean conditions were stable on large scales, they were also well mixed, which could disperse molecules before they interacted meaningfully. Sheltered environments countered this effect by offering pockets where chemistry could linger. Time spent together mattered more than speed of movement. Cycles were particularly influential in these regions. Tidal influence, even if weaker than today, introduced gentle repetition. Water levels rose and fell, temperatures shifted slightly, and chemical concentrations waxed and waned. Each cycle reinforced certain interactions while dissolving others. Over countless repetitions, these rhythms favored chemical arrangements capable of enduring change. On the seafloor, sediments acted as quiet archives. As particles settled, they carried with them chemical traces of the water above. These layers preserved conditions long after surface waters had moved on. Within sediments, reduced movement and limited exposure created stable microenvironments, where reactions could proceed slowly and steadily. Porous rocks beneath the seafloor extended this shelter even further. Water circulating through these spaces experienced controlled conditions, guided by pressure and temperature rather than waves or wind. Chemical gradients developed naturally as fluids moved from one region to another. These gradients represented stored energy, capable of driving reactions without the need for external input. Importantly, sheltered environments reduced extremes. They softened temperature fluctuations, shielded molecules from intense radiation, and moderated chemical shocks. This gentler setting allowed fragile compounds to persist longer than they would in harsher conditions. Persistence did not guarantee complexity, but it allowed it to be explored more thoroughly. The oceans at this time were still lifeless, yet these sheltered regions hinted at what might one day become habitats. They provided structure without design, protection without intention. Chemistry was free to unfold, guided by the environment rather than constrained by it. In these quiet spaces, the pace of change slowed just enough to allow subtle patterns to take hold. Over millions of years, these environments multiplied across the planet. Coastlines shifted, seafloors expanded, and new sheltered regions formed as tectonic processes reshaped the crust. Each new pocket offered another opportunity for chemistry to persist and interact. The oceans became increasingly diverse, not just in composition, but in structure. These settings did not compete with one another. Instead, they complemented the broader oceanic system. Open waters distributed materials globally, while sheltered environments refined them locally. Together, they created a balance between mixing and concentration, movement and stillness. This balance was essential for sustaining chemical complexity. As Earth continued its slow evolution, sheltered environments quietly accumulated importance. They did not announce themselves with dramatic events or visible transformations. Their influence lay in repetition, in patience, in allowing processes to continue without interruption. In their calm persistence, they offered chemistry the time and space it needed. By the end of this stage, the oceans were no longer uniform expanses of water. They were structured worlds, filled with niches defined by depth, movement, and protection. These sheltered environments had become integral parts of the planet's system, gently preparing the conditions that would one day support the earliest forms of life. 9. The first boundaries: primitive, cell-like structures. As chemistry continued to unfold within Earth's ancient oceans, a subtle but important shift began to occur. Among the countless molecules drifting through water and lingering on mineral surfaces, some began to form natural boundaries. These boundaries did not enclose life, nor did they function as true cells, but they introduced a new idea into Earth's chemical story: separation. With separation came stability, and with stability came the possibility of continuity. Water is an environment that encourages movement and mixing. While this fluidity allowed molecules to meet and interact, it also made it difficult for any organized system to persist. Reactions occurred, products formed, and then everything dispersed again. Over time, However, certain molecules demonstrated an unusual behavior. When placed in water, they naturally assembled into thin layers, arranging themselves so that part of the molecule faced the water while another part avoided it. These molecules, often described as having both water-loving and water-avoiding regions, did not require guidance to assemble. Their structure alone was enough. When present in sufficient numbers, they aligned side by side, forming sheets or spheres. In doing so, they created simple enclosures, trapping water and dissolved substances within. These enclosures were fragile, temporary, and constantly forming and dissolving, yet their repeated appearance marked a quiet turning point. Such structures are sometimes called protocells or vesicles, though at this stage they were not alive. They did not grow, reproduce, or metabolize in a biological sense. Instead, they represented a physical phenomenon arising naturally from chemistry. Their importance lay not in what they did, but in what they made possible. For the first time, chemistry could occur inside a defined space, separate from the surrounding ocean. These primitive boundaries changed the behavior of molecules inside them. Substances trapped within an enclosure remained together longer than they would in open water. Reactions could proceed without immediate dilution, allowing products to accumulate. This persistence increased the likelihood of further interaction, reinforcing chemical pathways that might otherwise fade away. Separation, even when temporary, proved to be powerful. The formation of these boundaries required no rare conditions. The building blocks were common, and the process occurred wherever suitable molecules encountered water. Shallow pools, mineral surfaces, and sediment-filled pores all supported their appearance. Each environment offered slightly different conditions, influencing the size, stability, and composition of the enclosures. Variation emerged naturally, not through selection, but through environmental diversity. Importantly, these structures were dynamic. They formed, merged, divided, and dissolved in response to changes in temperature, chemistry, and movement. Their boundaries were flexible rather than rigid, allowing substances to pass in and out. This permeability prevented isolation, while still maintaining a degree of separation. It was a balance between openness and containment. Inside these enclosures, chemistry unfolded differently. Concentrations of molecules could become higher than in the surrounding water. Energy gradients could be maintained across the boundary, with differences in composition between inside and outside. These gradients represented stored energy, capable of driving reactions. Though no enzymes or genetic material existed yet, the basic physical conditions that would later support metabolism were quietly assembling. The boundaries themselves also participated in chemistry. Molecules embedded within or attached to the enclosing layer could interact with substances on either side. In this way, the boundary became more than a wall. It became an interface. Reactions could be influenced by position, orientation, and proximity, adding another layer of organization to the system. Over time, certain enclosures proved more stable than others. Those composed of molecules that resisted disruption persisted longer, simply because they were less likely to fall apart. This persistence allowed internal chemistry to continue uninterrupted. While this was not biological selection, it introduced a kind of physical filtering, where stability favored continuity. Environmental cycles reinforced these effects. In tidal pools, repeated drying and rehydration stressed fragile structures while allowing more resilient ones to endure. Temperature fluctuations challenged boundaries, breaking some while strengthening others through rearrangement. Each cycle acted as a test, not imposed deliberately, but applied consistently by the environment itself. The presence of boundaries also altered how chemistry interacted with energy. Heat, light, and chemical gradients could influence reactions differently inside an enclosure than outside it. A boundary could buffer temperature changes or moderate exposure to radiation. In doing so, It created a slightly more controlled internal environment, even though control was not intentional. These early enclosures did not represent life, yet they introduced the fundamental concept of individuality. Each boundary defined an inside and an outside, a distinction that would later become central to biology. Even without genetic information or reproduction, these structures demonstrated that chemistry could be compartmentalized, organized, and sustained. Movement remained constant. Enclosures drifted through the water, carried by currents, colliding with one another and with mineral surfaces. Some merged into larger structures, combining their contents. Others split apart, distributing molecules into new configurations. The oceans, by this stage, had become laboratories of boundary formation. Countless enclosures appeared and disappeared, each one a brief experiment in organization. Most left no lasting trace, but their sheer number ensured that some would persist long enough for meaningful chemistry to occur within them. It is important to recognize how gentle this process was. There were no sudden leaps from non-life to life, no moment that could be identified as a beginning. Instead, there was continuity. Chemistry flowed smoothly into compartmentalization. Just as earlier motion flowed into pattern, each step built naturally upon the last. These primitive boundaries also interacted with sheltered environments in powerful ways. Within cracks, pores, and sediments, enclosures were protected from excessive disruption. There, they could persist longer, allowing internal processes to repeat and refine. Shelter and separation worked together, reinforcing stability. As Earth continued to change, these structures became more common and more diverse. Each variation represented a different way of maintaining separation while remaining connected to the environment. The oceans were slowly exploring the idea of containment. By the end of this stage, Earth had not yet produced living cells, but it had produced something essential: the habit of boundaries. The planet had learned how to divide space without halting interaction, how to create interiors without isolation. This ability would later become fundamental to life, but for now, it remained a quiet physical phenomenon. In the vast calm of the ancient seas, countless tiny enclosures formed and dissolved, each one briefly holding chemistry together. Their existence did not announce the arrival of life, but it prepared the conditions under which life could eventually emerge. The oceans, patient and unhurried, continued their slow work, shaping matter into ever more organized forms. 10. Metabolism, before life. As primitive boundaries became more common within Earth's ancient oceans, the chemistry unfolding inside them began to take on a new quality. Reactions no longer occurred only as isolated events, but sometimes linked together in loose sequences. One reaction produced a substance that fed into another, and energy released in one step could influence what followed. This stage did not yet involve life, but it introduced the quiet beginnings of metabolism, the organized processing of energy and matter. Metabolism, in its simplest sense, is not uniquely biological. It refers to sets of chemical reactions that occur in a coordinated way, allowing energy to flow and materials to be transformed. In the early oceans, such coordination arose naturally, wherever conditions allowed reactions to repeat reliably. Primitive enclosures, mineral surfaces, and chemical gradients all contributed to this emerging organization. Inside simple boundary structures, molecules remained together long enough for sequences of reactions to occur. A compound formed by chance might persist, encountering other molecules before drifting away or breaking apart. If the environment favored certain transformations, these reactions could recur again and again. Over immense spans of time, repetition gave rise to rudimentary chemical pathways. Energy was essential to these processes. Without a steady input, reactions would stall, and systems would drift toward equilibrium. In the ancient oceans, energy was abundant. Sunlight warmed surface waters. Geothermal heat flowed upward from below, and chemical gradients stored potential energy throughout the environment. These sources did not act in isolation. They overlapped and reinforced one another, ensuring that reactions could proceed under a wide range of conditions. Some reactions released energy, while others required it. When these two types occurred close together, the energy from one could drive the other. This coupling was not intentional, but it was effective. Over time, certain reaction pairs became more common simply because they could proceed under prevailing conditions. These early couplings resembled the foundations of metabolic processes, though they lacked the specificity and efficiency of modern biology. Minerals played a particularly important role in these early systems. Surfaces rich in metals such as iron and nickel could facilitate reactions by bringing molecules into close proximity and stabilizing intermediate forms. These catalytic effects allowed reactions to occur more readily than they would in open water. In doing so, minerals acted as quiet partners in the development of organized chemistry. Within sheltered environments, such as pores in rock or sediment-filled basins, conditions remained stable enough for these processes to persist. Fluctuations in temperature or chemistry were softened, allowing reaction sequences to continue without frequent disruption. Stability favored continuity, and continuity allowed chemistry to explore increasingly complex arrangements. The concept of metabolism before life can be understood as a pattern rather than a system. There were no enzymes, no genetic instructions, and no self-maintaining organisms. Instead, there were networks of reactions that happened to reinforce one another. When conditions changed, these networks dissolved, only to form again elsewhere under similar circumstances. One of the most important aspects of these early metabolic-like processes was their relationship with boundaries. Primitive enclosures helped maintain internal conditions different from the surrounding environment. Concentrations of molecules could be higher inside, and energy gradients could be sustained across the boundary. These differences allowed reactions to proceed that might not occur in open water. Boundaries also introduced a degree of individuality. While none of these environments were alive, they demonstrated how separation could support organized chemical activity. Some enclosures persisted longer than others, not because they were selected, but because their composition made them more stable. The movement of matter between inside and outside remained essential. Boundaries were permeable, allowing substances to flow in and out. This exchange prevented isolation and ensured that internal chemistry remained connected to the broader environment. Energy and materials could enter, be transformed, and exit again, maintaining dynamic balance. Cycles played a key role in sustaining these early processes. Daily temperature changes, tidal movements, and periodic drying and rehydration all influenced reaction pathways. Each cycle provided opportunities for reactions to begin, pause, or restart. Over time, cycles reinforced patterns that could endure change, favoring reactions compatible with fluctuation. These early metabolic patterns did not consume resources in a biological sense. They did not grow or replicate themselves. Instead, they existed as long as conditions allowed. When energy sources shifted or boundaries dissolved, the processes ended. Yet the memory of these processes remained in the environment, ready to reappear when conditions aligned again. Importantly, metabolism before life did not progress toward a goal. There was no inevitable march toward complexity. Instead, chemistry explored possibilities freely, constrained only by physical laws. Some arrangements proved stable and recurred often, while others remained rare or fleeting. Over vast timescales, the cumulative effect was an increase in organized chemical activity. The oceans acted as reservoirs for these processes. They absorbed the products of reactions, redistributed materials, and provided a stable backdrop against which chemistry could unfold. Even when individual reaction networks ended, their components returned to the broader system, available for reuse. Nothing was wasted, Everything was recycled. As Earth continued to cool and stabilize, the range of environments supporting metabolic-like chemistry expanded. More sheltered regions formed. Energy flows became more predictable, and chemical inventories grew richer. The planet was becoming increasingly capable of supporting sustained chemical organization. By this stage, Earth had developed all the fundamental ingredients required for true metabolism: energy flow, chemical diversity, compartmentalization, and stability. What remained absent was life's defining feature: the ability to maintain and reproduce itself through encoded information. Metabolism before life was not a precursor in the sense of a blueprint, but in the sense of practice. The planet was learning how to move energy through matter in organized ways. Each reaction sequence was a rehearsal, each boundary a temporary stage. In the calm persistence of ancient oceans, chemistry flowed, transformed, and repeated. Energy moved through systems that had no awareness of what they were becoming. And in that quiet continuity, Earth took another patient step toward a living planet. 11. The emergence of the first true organisms. Over immense stretches of time, as chemistry continued its quiet exploration within Earth's oceans, a subtle transition began to take shape. The difference between non-living systems and living ones did not arrive as a sharp boundary, but as a gradual blending of properties. What emerged was not sudden life, but continuity that became increasingly self-sustaining. In this long, patient process, the first true organisms slowly appeared. The environments that supported this transition were already well prepared. Energy flowed steadily through oceans, warmed from above and below. Chemical diversity was abundant, shaped by volcanic input, mineral surfaces, and countless reactions unfolding in water. Primitive boundaries allowed chemistry to remain localized, and metabolic-like networks had demonstrated that reactions could link together in stable ways. All the ingredients were present, waiting only for a particular kind of organization. The defining feature of the first organisms was not complexity, but persistence. These early entities were simple beyond modern comparison, likely consisting of little more than a boundary enclosing a small network of reactions. What set them apart was their ability to maintain themselves for longer periods by continuously processing energy and materials from their surroundings. They did not merely form and dissolve, they endured. At the heart of this endurance was the ability to harness chemical reactions in a way that supported the structure enclosing them. Energy released from reactions could be used to maintain internal conditions, reinforcing the boundary rather than allowing it to fall apart. In this way, chemistry and structure became linked in a self-supporting loop. These first organisms were almost certainly microscopic and aquatic, existing entirely within the ancient oceans. They did not require oxygen, which was absent from the environment, and they relied instead on chemical energy derived from their surroundings. Compounds such as hydrogen, sulfur, and simple carbon-based molecules provided the raw materials for their internal reactions. Life began quietly, adapted to conditions that would later become rare. The boundaries enclosing these organisms were flexible and dynamic, allowing substances to move in and out while maintaining a distinct internal environment. This permeability was essential. Without exchange, internal chemistry would stagnate. Within these early organisms, reaction networks became more consistent. Certain sequences of reactions occurred repeatedly, supported by internal conditions that favored their continuation. These reactions transformed environmental materials into forms useful for maintaining structure and energy flow. In this way, the organism interacted with its surroundings not passively, but actively, altering nearby chemistry as it persisted. Reproduction, in its earliest form, was not a precise or reliable process. Instead of deliberate replication, early organisms likely grew as materials accumulated inside them. When boundaries became unstable due to size or environmental stress, they could divide, producing two smaller structures. Each new structure carried with it a portion of the internal chemistry, allowing processes to continue independently. This division was uneven and unpredictable, but it allowed continuity across generations. Variation emerged naturally through this process. No two divisions were identical, and internal chemistry differed slightly from one organism to another. Some configurations persisted longer than others, simply because they were more stable under prevailing conditions. Over time, this variation influenced which forms became more common, though without intention or foresight. The oceans provided a forgiving environment for these early organisms. Water buffered temperature changes, diluted waste products, and supplied a constant source of materials. Sheltered regions, such as sediments and shallow basins, offered additional protection, allowing organisms to persist even as conditions shifted elsewhere. Life did not spread rapidly. It settled slowly where stability allowed. These first organisms were not alone for long. As they persisted and reproduced, they altered their immediate surroundings. Chemical byproducts accumulated, changing local conditions. Some of these changes made environments less hospitable for certain organisms, while others created new opportunities. In this way, life began to influence its environment even at this early stage. Communication between organisms did not exist, nor did cooperation in any meaningful sense. Each organism functioned independently, guided by its internal chemistry and the conditions around it. Yet through shared environments, they indirectly influenced one another. Competition was minimal, not because it was avoided, but because resources were abundant and life was sparse. Time remained the dominant factor. The emergence of the first organisms likely took hundreds of millions of years. Progress was slow, marked by countless failed attempts and fleeting forms. Yet success did not require speed. It required only that some configurations persist long enough to reproduce and continue. The simplicity of these organisms should not be mistaken for fragility. Though lacking complexity, they were well suited to their environment. Their chemistry matched the conditions of the ancient oceans, and their boundaries functioned effectively within those constraints. In this sense, they were highly adapted, even without evolution as we understand it today. As life established itself, the distinction between living and non-living chemistry became clearer. Living systems actively maintained internal organization, drawing energy from their surroundings to resist decay. Non-living systems, by contrast, drifted toward equilibrium. This difference marked a fundamental shift in Earth's processes, though it unfolded so gradually that no single moment defined it. The presence of life did not immediately transform the planet. For vast stretches of time, life remained sparse and simple. The oceans still looked much as they had before, and geological processes continued largely unchanged. Yet beneath the surface, something profound had occurred. Earth was no longer merely a chemical system. It had become a biological one. These first organisms laid the foundation for all life that would follow. Their methods of energy use, boundary maintenance, and interaction with the environment would be refined and expanded over billions of years. Yet at this early stage, life was content to persist quietly, shaped by the conditions that gave rise to it. In the calm depths of the ancient oceans, the first true organisms lived without awareness of their significance. They processed energy, maintained structure, and divided when conditions allowed. Their existence was not dramatic or visible, but it was enduring. And in that endurance, Earth took one of its most meaningful steps, becoming a planet where life could continue. 12. Life without oxygen. In the world that welcomed the first organisms, oxygen was almost entirely absent. The ancient oceans and atmosphere bore little resemblance to those of the modern Earth, and life arose adapted to this very different chemistry. For these earliest organisms, oxygen was neither necessary nor useful. Instead, it would have been harmful. Life began in a planet-wide environment defined by scarcity of oxygen and abundance of alternative chemical pathways. The early atmosphere contained gases released from volcanic activity, including carbon dioxide, nitrogen, methane, and traces of hydrogen and sulfur compounds. Oxygen, though present in tiny amounts from the breakdown of water by sunlight, was quickly consumed by reactions with exposed rock and dissolved metals. As a result, free oxygen could not accumulate. The oceans reflected this state, remaining anoxic, or oxygen-free, from surface to depth. The first organisms were shaped entirely by these conditions. Their internal chemistry relied on reactions that did not require oxygen and often would not function in its presence. Energy was obtained through anaerobic processes, meaning chemical pathways that operate without oxygen as an electron acceptor. These processes were less efficient by modern standards, but they were sufficient for simple, slow-growing life. Many early organisms likely depended on chemical compounds abundant in their environment. Hydrogen, produced by volcanic processes and chemical reactions within the crust, served as a common energy source. Sulfur compounds, particularly hydrogen sulfide, were also widely available and chemically reactive. Carbon dioxide, dissolved in seawater, provided a ready source of carbon for building molecular structures. Within these organisms, chemical reactions transferred electrons between molecules, releasing energy that could be used to maintain structure and drive internal processes. Instead of oxygen, other substances filled the role of electron acceptors. These included sulfur, iron, and carbon compounds. Such reactions were well suited to the chemistry of the ancient oceans, where reduced compounds were plentiful. Iron played a particularly important role in this oxygen-free world. Dissolved iron was abundant in seawater, remaining soluble in the absence of oxygen. Early organisms interacted with this iron, sometimes using it directly in their metabolic processes. Over time, these interactions would leave geological traces, recording the long history of anaerobic life. Life without oxygen was not restricted to isolated niches. It was the dominant form of life on Earth for a vast span of time, lasting well over 1 billion years. During this era, all known organisms were anaerobic, and the planet functioned entirely under this regime. Oxygen, when it eventually appeared in greater quantities, would represent a profound challenge, rather than an immediate benefit. Anaerobic organisms tended to grow slowly and steadily, without access to the high energy yields of oxygen-based metabolism. Their energy budgets were modest. This limitation kept life small and simple, but it also encouraged efficiency. These organisms made careful use of available resources, maintaining internal stability rather than rapid expansion. The oceans provided a stable environment for anaerobic life. Water buffered changes in temperature and chemistry, allowing organisms to persist even as conditions fluctuated. Sheltered regions, such as sediments and mineral-rich areas, offered additional protection and consistent access to chemical energy sources. Life spread gradually, following the availability of suitable conditions. Waste products from anaerobic metabolism accumulated in the environment. Over time, these substances influenced planetary chemistry, altering the composition of air and water. Even in its simplest forms, life began to shape its surroundings. Despite the absence of oxygen, the oceans were far from stagnant. Chemical gradients, currents, and energy flows continued to drive movement and interaction. Anaerobic organisms occupied niches defined by these gradients, clustering where energy sources were most accessible. Some favored the seafloor, where chemical inputs from the crust were strongest, while others persisted in shallow waters. The relationship between life and environment during this era was intimate and immediate. Without complex regulatory systems, organisms responded directly to changes in chemistry and energy availability. When conditions were favorable, they persisted and reproduced. When conditions shifted beyond their tolerance, they faded away. Adaptation occurred slowly, through countless small variations over immense timescales. The simplicity of anaerobic life allowed it to endure harsh conditions. Many such organisms could tolerate extremes of temperature, acidity, and chemical composition. This resilience enabled life to persist through geological changes that might have extinguished more complex forms. In this sense, early life was well matched to a restless planet. Importantly, life without oxygen established the biochemical foundations upon which later life would build. Core metabolic pathways, methods of energy transfer, and strategies for maintaining internal order all emerged during this anaerobic era. Even organisms that would later adapt to oxygen retained traces of these ancient processes within their cells. The absence of oxygen also preserved certain chemical possibilities that would later disappear. Many reactions that occur readily in oxygen-free environments are suppressed or altered when oxygen is present. During this early period, chemistry and biology explored pathways that would later become rare or confined to specialized niches. For much of Earth's history, anaerobic life was the only life. It did not rush toward complexity, nor did it transform the planet rapidly. Instead, it persisted quietly, maintaining itself and gradually increasing in diversity. The oceans remained largely unchanged in appearance, even as they hosted an ever-growing microbial world. Over time, some organisms developed new ways of interacting with energy, including the ability to harness sunlight. These innovations would eventually alter the planet in fundamental ways. Yet even as these changes began, anaerobic life continued to thrive, adapting to new conditions rather than disappearing. Life without oxygen represents one of the longest and most stable chapters in Earth's history. Instead, life emerges where chemistry and energy allow, shaped by the environment rather than aspiring to change it. In the quiet depths of the ancient oceans, anaerobic organisms lived and multiplied, processing chemicals, releasing byproducts, and persisting across deep time. Their existence was neither dramatic nor fleeting. It was enduring, steady, and foundational. Through them, Earth learned how to be alive long before oxygen transformed the world. Part 13, The Role of Microbes in Shaping the Oceans. As anaerobic life became established across Earth's ancient oceans, the planet entered a new phase of quiet transformation. The earliest organisms were small and simple, yet their collective presence began to influence the chemistry of the seas in subtle but lasting ways. Individually, each microbe altered only its immediate surroundings. Together, over immense spans of time, they reshaped the oceans themselves. These early microbes lived immersed in water that carried dissolved minerals, gases, and chemical gradients inherited from Earth's geological processes. By drawing energy from these compounds, microbes participated directly in the movement of matter through the oceans. They consumed certain substances, transformed them internally, and released altered products back into the surrounding water. In doing so, life became a new participant in Earth's chemical cycles. One of the most significant changes driven by microbes involved carbon. Carbon dioxide, dissolved in seawater, served as a primary carbon source for many early organisms. Through their metabolic processes, microbes incorporated carbon into organic molecules, temporarily removing it from the inorganic pool. When these organisms died or released waste, much of that carbon returned to the environment in altered forms. This cycling, repeated countless times, gradually changed the balance of carbon compounds in the oceans. Sulfur compounds were also deeply influenced by microbial activity. Hydrogen sulfide, abundant in oxygen-free environments, provided a rich source of chemical energy. Certain microbes specialized in using sulfur compounds to fuel their metabolism, converting them into other forms in the process. These transformations altered the chemical landscape, creating gradients that could support additional life forms. Sulfur cycling became an enduring feature of the oceans, linking geology and biology. Iron, long present in dissolved form within the anoxic oceans, interacted closely with microbial life. Some microbes influenced the chemical state of iron through their metabolic processes, causing it to shift between soluble and insoluble forms. Over time, these interactions contributed to the deposition of iron-rich sediments on the sea floor. Such deposits recorded the ongoing dialogue between life and environment, even though the organisms themselves left no visible traces. Microbial activity did not occur evenly across the oceans. Life clustered where energy sources were most accessible, such as near hydrothermal systems, within sediments, and in shallow waters. These localized concentrations of life intensified chemical transformations in specific regions. Over time, ocean currents redistributed the products of these transformations, spreading their influence far beyond their point of origin. The oceans responded slowly to these changes, integrating them over long durations. Unlike the atmosphere, which can change relatively quickly, the oceans act as vast reservoirs, absorbing and moderating inputs. As microbes altered chemical balances, the oceans adjusted gradually, maintaining stability while accommodating new patterns. This slow response allowed life to persist without destabilizing the environment that supported it. As microbial populations expanded, competition for resources remained minimal. The oceans were large, and life was sparse. Energy sources such as hydrogen, sulfur compounds, and dissolved carbon dioxide were abundant. This abundance allowed multiple metabolic strategies to coexist, increasing the diversity of microbial life without forcing rapid exclusion. Diversity arose through variation rather than conflict. The influence of microbes extended beyond chemistry to physical processes as well. Organic matter produced by microbes eventually settled toward the seafloor, contributing to sediment formation. These sediments altered the structure of the ocean floor, influencing water movement and chemical exchange between crust and ocean. In this way, life participated indirectly in shaping Earth's physical features. Despite these influences, the oceans retained their overall character. They remained oxygen-free, mineral-rich, and governed primarily by geological processes. Life did not yet dominate the planet. It blended into existing systems, adding complexity without overwhelming them. This integration allowed Earth to remain stable even as biology took root. Microbial life also introduced feedback loops into the system. By consuming certain compounds, microbes reduced their availability, potentially limiting further growth. At the same time, their waste products created new energy sources for other organisms. These interactions fostered networks of dependency that increased the resilience of the microbial ecosystem. Stability emerged not from uniformity, but from interconnectedness. Over time, microbial activity influenced the acidity of seawater. Carbon cycling, in particular, affected the balance between acidic and basic compounds. Though changes were slight on short timescales, they accumulated over millions of years. The ocean's pH shifted gradually, shaping which chemical reactions were favored and which organisms could thrive. The persistence of microbes ensured that chemical transformations were continuous. Unlike geological events, which can be episodic, biological activity occurred without pause. Day and night, shallow and deep, microbes processed energy and matter, maintaining a steady background of change. This constancy made biology a reliable component of Earth's systems. As microbial life spread, it also adapted to diverse conditions. Variations in temperature, chemistry, and pressure encouraged specialization. Some microbes favored warm environments near the seafloor, while others thrived in cooler waters. This adaptability increased the range of environments influenced by life, expanding its planetary footprint. Yet, even as life diversified, it remained invisible on a global scale. There were no forests, reefs, or blooms to mark its presence. The oceans looked much the same as they had before life emerged. Only through chemical signatures and sedimentary records did the influence of microbes become apparent. Over hundreds of millions of years, the continuous activity of microbes subtly altered the balance of Earth's systems. Elements cycled differently, sediments formed with new characteristics. These changes set the stage for further biological innovation, even though such innovations were not yet inevitable. One of the most profound consequences of microbial activity lay still in the future. Some microbes would eventually evolve ways to harness sunlight in a manner that released oxygen as a byproduct. When that happened, the oceans and atmosphere would change dramatically. For now, however, microbial life worked within the oxygen-free world it had inherited. In this long chapter of Earth's history, microbes acted as quiet engineers. They did not reshape the planet through force or speed, but through persistence. Each reaction, each cycle, each organism contributed a small adjustment. Over deep time, these adjustments accumulated, ensuring that life and planet evolved together. By shaping the oceans chemically and physically, microbes transformed Earth from a world where life merely existed into one where life and environment were inseparable. The oceans became living systems, not because they teemed with visible organisms, but because their chemistry now bore the imprint of biology. And in that subtle transformation, Earth moved steadily toward its next great change. 14. Cyanobacteria and the first light harvesters. As microbial life continued its quiet work within the ancient oceans, a remarkable innovation slowly took shape. Among the countless anaerobic organisms drifting through water and settling into sediments, some began to interact with sunlight in a new and transformative way. This interaction did not arise suddenly, nor did it immediately change the world. Instead, it emerged gradually, refining itself over immense spans of time. These organisms, known today as cyanobacteria, became the first true harvesters of light. Sunlight had always reached the surface of the oceans, warming the water and driving chemical reactions. For most of Earth's history up to this point, light was simply another source of energy influencing non-living chemistry. Cyanobacteria introduced a new possibility, capturing light energy and converting it into chemical energy stored within molecular bonds. This process, though simple in its earliest forms, represented a profound shift in how life interacted with its environment. Early light-harvesting organisms were still microbial and aquatic, lacking nuclei or complex internal structures. They lived entirely within water, often forming thin layers in sunlit regions. Their boundaries enclosed chemical systems capable of absorbing photons and using that energy to drive internal reactions. In doing so, they reduced their reliance on chemical energy sources supplied by the environment, such as hydrogen or sulfur compounds. The mechanism these organisms developed involved pigments capable of absorbing light. These pigments captured specific wavelengths of sunlight and transferred that energy into chemical pathways inside the cell. Over time, this system became more refined and reliable. Light, once an external influence, became an internal resource, accessible whenever conditions allowed. Crucially, the form of light harvesting that would eventually dominate involved the splitting of water molecules. In this process, water served as a source of electrons, allowing carbon dioxide to be converted into organic molecules. The byproduct of this reaction was oxygen. At first, the release of oxygen was minimal, quickly absorbed by surrounding water and reacting with dissolved metals. Its presence went largely unnoticed. Cyanobacteria did not set out to produce oxygen, nor did oxygen benefit them initially. For these organisms, oxygen was simply a consequence of an efficient way to use water and sunlight. The oceans, rich in water and exposed to light, provided an abundant and reliable setting for this process. Over time, cyanobacteria spread wherever light reached, expanding slowly but steadily. Life powered by sunlight had important advantages. Unlike chemical energy sources, which could be limited or localized, sunlight was broadly available across the planet's surface. This allowed cyanobacteria to occupy vast regions of the oceans, particularly shallow waters. Their growth remained slow by modern standards, but their persistence ensured gradual expansion. As cyanobacteria multiplied, their collective activity began to influence ocean chemistry in new ways. Oxygen released during photosynthesis reacted readily with dissolved iron, causing it to precipitate out of solution. This process removed iron from seawater and deposited it as solid minerals on the seafloor. Over time, these deposits accumulated in thick layers, silently recording the rise of oxygenic photosynthesis. The oceans responded slowly to this new input. Instead, it was consumed by reactions with iron, sulfur, and other reduced compounds. For a long period, the planet's systems absorbed oxygen as quickly as it was produced. Life continued much as it had before, with anaerobic organisms still dominant. Yet the balance was shifting. Each generation of cyanobacteria added a little more oxygen to the environment. As reactive substances were gradually depleted, oxygen began to persist for longer periods. The ocean's chemistry started to change. Not abruptly, but steadily. Regions near active photosynthesis experienced conditions increasingly different from the deep, oxygen-free waters below. Cyanobacteria also influenced carbon cycling in new ways. By using light to fix carbon dioxide into organic matter, they altered the distribution of carbon between ocean, atmosphere, and sediments. Organic material produced by these microbes settled to the seafloor, where it could be buried and preserved. This burial removed carbon from circulation, contributing to long-term changes in atmospheric composition. Despite these changes, cyanobacteria themselves remained simple. They did not form complex communities or large structures. They lived as single cells or loose mats, drifting or resting on surfaces. Their success lay not in complexity, but in reliability. Sunlight rose each day, water remained abundant, and their chemistry worked. The spread of light-harvesting life introduced new gradients into the oceans. Surface waters became chemically distinct from deeper layers. Oxygen, though still limited, appeared near the surface. These gradients created new niches, allowing different forms of life to coexist. Anaerobic organisms retreated to deeper or sheltered environments, while photosynthetic microbes thrived where light was available. This coexistence persisted for a long time. The rise of photosynthesis did not eliminate earlier life forms. Instead, it added complexity to the system, layering new processes atop old ones. Earth's biosphere grew richer, not by replacement, but by accumulation. The influence of cyanobacteria extended beyond the oceans. As oxygen slowly accumulated, trace amounts began to escape into the atmosphere. There, it reacted with gases and altered atmospheric chemistry. Though still far from oxygen-rich, the air was beginning to change. These changes would eventually have profound consequences, but at this stage, they unfolded quietly. Photosynthesis also affected Earth's energy balance. By capturing sunlight and storing it in chemical bonds, cyanobacteria introduced a new way of moving energy through the planet. This stored energy would later support more complex life forms. But even now, it influenced the distribution of matter and energy across Earth's systems. It is important to recognize how long this process took. The emergence and spread of cyanobacteria unfolded over hundreds of millions of years. There was no sudden transformation, no visible tipping point. From the perspective of deep time, photosynthesis rose slowly, almost imperceptibly, yet its effects were cumulative and enduring. For much of this era, Earth remained an anaerobic world. Oxygen was a minor component, confined to certain regions and quickly consumed. Yet the foundation for a more dramatic transformation had been laid. Cyanobacteria had demonstrated that light could power life on a planetary scale. In the calm shallows of ancient seas, mats of photosynthetic microbes absorbed sunlight day after day. They released oxygen molecule by molecule, unaware of its significance. Their existence was unassuming, their pace unhurried. And yet, through their persistence, they initiated one of the most important changes in Earth's history. By harvesting light, cyanobacteria expanded the possibilities of life. They transformed sunlight from a background influence into a biological resource. In doing so, they quietly prepared the planet for the next great transition, one that would alter the oceans, the atmosphere, and the future of life itself. 15. Slow changes in the ancient seas. As cyanobacteria continued their quiet work near the surface of Earth's oceans, the effects of their activity began to accumulate in ways that were not immediately visible. The ancient seas did not change suddenly or dramatically. Instead, they responded slowly, integrating the steady input of oxygen into systems that had been shaped for billions of years without it. These changes unfolded at a pace so gradual that entire eras passed while the oceans adjusted. For a long time, the oxygen released by photosynthetic microbes never traveled far. It dissolved into surrounding water and reacted almost immediately with abundant reduced substances, particularly dissolved iron and sulfur compounds. These reactions removed oxygen from circulation, binding it into solid minerals that settled onto the seafloor. The oceans acted as vast chemical buffers, absorbing change and maintaining stability even as new processes emerged. Iron played a central role in this transformation. In the oxygen-free oceans of earlier eras, iron remained dissolved and mobile. As oxygen began to appear, it reacted with this iron, forming insoluble compounds that precipitated out of the water. Layer upon layer of iron-rich sediments accumulated, quietly recording the gradual presence of oxygen. These deposits formed slowly, often over millions of years, reflecting the steady pace of planetary change. As reactive substances were consumed, the capacity of the oceans to absorb oxygen began to decline. Oxygen lingered slightly longer in surface waters, especially in regions where cyanobacteria were most active. This persistence marked the beginning of a new chemical landscape. Though still limited, oxygen became a recurring feature rather than a fleeting anomaly. The vertical structure of the oceans grew more pronounced during this time. Surface waters, influenced by sunlight and photosynthesis, began to differ chemically from deeper layers. Oxygen appeared near the surface, while the depths remained anoxic. This stratification created new gradients, influencing circulation patterns and chemical reactions. The oceans became layered not only by temperature and density, but by chemistry. These changes affected microbial life in subtle ways. Anaerobic organisms, which had thrived for eons, continued to dominate vast regions of the oceans. Yet near the surface, oxygen-sensitive microbes faced new challenges. Some retreated to deeper waters or sheltered environments where oxygen remained scarce. Others adapted, developing ways to tolerate or avoid oxygen's reactive effects. At the same time, oxygen opened new possibilities. Though initially harmful to many organisms, oxygen offered a powerful means of extracting energy from organic molecules. This potential would not be fully realized until much later, but its presence began to reshape the energetic landscape. Life and environment entered a period of adjustment, responding to changes that would ultimately redefine the planet. The oceans themselves moderated these transitions. Their immense volume diluted oxygen, preventing rapid accumulation. Currents mixed surface waters with deeper layers, spreading chemical changes slowly. Even as oxygen production increased, its effects remained localized for long periods. The seas absorbed the impact of biological innovation, allowing Earth to change without destabilizing itself. Carbon cycling also shifted during this era. As photosynthetic organisms fixed carbon dioxide into organic matter, some of that material was buried in sediments rather than recycled immediately. This burial removed carbon from the active system, subtly altering the balance between atmosphere and ocean. Over time, these changes influenced climate and ocean chemistry, reinforcing the long-term effects of photosynthesis. The acidity of seawater responded gradually as well. Interactions between carbon dioxide, water, and newly formed oxygen compounds altered the balance of acids and bases. These shifts were slight but persistent, shaping which chemical reactions were favored and which organisms could thrive. The oceans remained hospitable, but their character evolved steadily. Despite these transformations, the overall appearance of the oceans remained familiar. They were still vast, deep, and largely unchanged at the surface. There were no large organisms, no visible signs of life beyond microbial films and mats. The drama of change occurred at the molecular and chemical level, invisible without instruments and patience. Geological processes continued alongside biological ones. Tectonic activity reshaped seafloors, volcanic eruptions introduced new materials, and erosion delivered minerals from emerging land masses. These inputs interacted with the changing chemistry of the oceans, adding complexity to an already intricate system. Earth's evolution remained a collaboration between life and geology. Over millions of years, the gradual accumulation of oxygen began to reach a threshold. The most reactive substances in the oceans were increasingly tied up in sediments, reducing their ability to remove oxygen from circulation. This shift did not happen everywhere at once. Different regions progressed at different rates, creating a patchwork of chemical environments across the globe. The atmosphere, though still largely oxygen-free, began to reflect these changes faintly. Small amounts of oxygen escaped from the oceans into the air, where it reacted with gases and sunlight. These interactions laid the groundwork for further atmospheric transformation, including the eventual formation of an ozone layer. Life continued to adapt quietly. Microbial communities diversified, occupying niches defined by new gradients of oxygen and chemistry. Some organisms specialized in environments where oxygen was present intermittently, developing strategies to survive its reactive nature. Others remained strictly anaerobic, persisting in stable, oxygen-free refuges. The pace of change during this era exemplified Earth's capacity for gradual transformation. The planet adjusted step by step, allowing systems to respond and stabilize before further change occurred. This patience ensured continuity, preventing abrupt disruptions that might have extinguished emerging life. In this long interval, the ancient seas were neither fully transformed nor unchanged. They existed in transition, carrying the imprint of both their anoxic past and their oxygenated future. Each wave, each current, moved through water that had been subtly altered by life's growing influence. By the end of this stage, oxygen had not yet reshaped the planet entirely, but it had become a permanent presence. The oceans were different than they had been before, even if those differences were nearly imperceptible. Life had begun to leave a lasting mark on Earth's chemistry, setting the stage for transformations yet to come. In the quiet depths and sunlit shallows, the seas continued their slow evolution. They absorbed change with patience, integrating new processes into old rhythms. And in that steady adjustment, Earth moved closer to a world where life and environment would be inseparable on every scale. 16. The deep time rhythm of early life. As oxygen slowly began to appear in parts of the oceans, early life continued to exist within a rhythm defined not by rapid change, but by extraordinary patience. For vast stretches of time, life on Earth remained simple, microscopic, and largely unchanged in outward form. Yet beneath this apparent stillness, a steady pulse of activity persisted, shaped by cycles of energy, chemistry, and planetary motion. This was the deep time rhythm of early life, a tempo measured not in years or centuries, but in millions of years. Microbial life spread gradually across the oceans, occupying environments that suited its chemical needs. Some thrived near the surface, where sunlight powered photosynthesis, while others remained in the depths, relying on chemical energy sources. Still others found stability within sediments or along mineral-rich seafloors. Each habitat supported its own quiet community, adapted to local conditions, yet connected through the movement of water and matter. Despite the growing diversity of microbial strategies, the overall pace of biological change remained slow. Generations passed without dramatic innovation, and lineages persisted with little alteration. This stability was not a sign of stagnation, but of balance. Early life existed in close harmony with its environment, shaped by constraints that favored endurance over rapid expansion. Environmental cycles played a central role in maintaining this rhythm. Seasonal variations, though less pronounced than today, influenced temperature and circulation. On longer timescales, tectonic activity reshaped seafloors, while volcanic eruptions introduced new materials into the oceans. Life responded to each cycle not with urgency, but with quiet adjustment. The oceans themselves acted as regulators of change. Their immense volume buffered temperature fluctuations, diluted chemical inputs, and smoothed transitions. Even as oxygen production increased, its effects were moderated by the sea's capacity to absorb and redistribute substances. This buffering allowed life to adapt gradually, reducing the risk of widespread disruption. Within microbial communities, interactions remained simple. There were no predators in the modern sense, no complex food webs. Energy flowed primarily through chemical and photosynthetic pathways, supporting slow growth and steady persistence. Competition existed, but it unfolded gently, governed by availability of energy rather than aggressive exclusion. Reproduction occurred continuously, yet without dramatic bursts. Cells divided, passed on their chemical systems, and continued existing within familiar constraints. Variation arose through small changes, but the environment favored those forms that could maintain stability. Over deep time, this resulted in gradual refinement rather than rapid diversification. The rhythm of early life was closely tied to geochemical cycles. Carbon, sulfur, iron, and other elements moved through the oceans and sediments, influenced by both geological processes and biological activity. Life participated in these cycles, but it did not yet dominate them. Instead, it blended into the planet's existing systems, contributing to slow, cumulative change. Sediments accumulating on the seafloor captured traces of this rhythm. Layer by layer, they recorded variations in chemistry, mineral composition, and biological influence. Each layer represented a moment in time, preserved quietly beneath the water. Together, these layers formed a long archive of Earth's early biosphere, written slowly and without interruption. The persistence of life during this era demonstrates the importance of continuity. Rather than seeking novelty, early life thrived by maintaining what worked. This conservatism allowed organisms to survive environmental fluctuations that might have eliminated more specialized forms. Stability was not a limitation, it was a strategy. Oxygen, though increasingly present in some regions, did not yet disrupt this rhythm entirely. Anaerobic and photosynthetic organisms coexisted, each occupying niches defined by chemistry and energy availability. The oceans supported this diversity by maintaining gradients and refuges. Life adjusted its pace to the environment, rather than forcing the environment to change abruptly. From a modern perspective, this period might seem uneventful. There were no animals, no plants, no visible ecosystems. Yet in terms of duration, it represents the majority of Earth's biological history. Life spent far more time as simple microbes than it ever has as complex organisms. This long interval shaped the foundations upon which all later life would depend. The slow rhythm of early life also allowed Earth systems to co-evolve with biology. As microbes altered ocean chemistry, the planet responded through geological and chemical processes. These responses, in turn, influenced life's possibilities. This feedback unfolded gradually, ensuring that neither life nor environment overwhelmed the other. Patience was the defining characteristic of this era. Change occurred, but it was measured and cumulative. Each generation inherited a world only slightly different from the one before. Over millions of years, these small differences added up. This rhythm extended across the entire planet. From sunlit shallows to dark depths, life persisted in a steady pattern. The oceans pulsed with quiet activity, unseen yet constant. Currents moved, reactions occurred, cells divided. As Earth approached future transitions, including more widespread oxygenation, this rhythm provided resilience. Life had learned how to endure, how to adjust slowly, and how to persist through change. These lessons, encoded not in consciousness but in chemistry, would prove essential for surviving the transformations yet to come. In the deep time rhythm of early life, there was no urgency, no destination. There was only continuation. Life existed because conditions allowed it, and it continued because it could. The oceans carried this rhythm forward, wave after wave, era after era. By understanding this long, quiet chapter, it becomes clear that life's success on Earth was not built on speed or complexity, but on patience. The earliest life forms set a tempo that matched the planet itself, ensuring that when greater changes arrived, life would be ready to meet them without losing its continuity. 17 fossil traces in stone and sediment. As early life continued its steady existence within the ancient oceans, it left behind almost no obvious signs of its presence. These organisms were small, soft, and simple, lacking hard parts that could easily be preserved. Over deep time, stone and sediment became quiet record keepers, preserving subtle evidence of life's earliest chapters. Fossils from this era do not resemble the familiar shapes of shells, bones, or leaves. Instead, they are chemical, textural, and structural impressions, formed gradually as sediments settled and hardened. Each layer of sediment captured a moment in time, recording the conditions of the ocean above it. Within these layers, the influence of microbial life was written not in form, but in pattern. One of the most enduring records of early life comes from layered rock structures known as stromatolites. These formations arose where microbial communities grew in shallow waters, trapping and binding fine particles of sediment. As microbes lived and reproduced, sediment accumulated around them, forming thin layers. Over long periods, these layers stacked upon one another, creating domed or column-like structures. Stromatolites did not form quickly. Their growth required stability, shallow water, and patience. Each layer represented a long interval of microbial activity, interrupted occasionally by changes in water level or sediment supply. The microbes themselves did not build with intention. Their everyday existence, repeated endlessly, was enough to shape stone. These structures provide some of the clearest physical evidence of early life. Found in rocks billions of years old, stromatolites reveal that microbial communities were widespread and persistent. Their presence confirms that life had become an integral part of shallow marine environments, interacting continuously with sediment and water. Beyond visible structures, early life left chemical signatures within rocks. As microbes processed elements such as carbon, sulfur, and iron, they altered the ratios of different isotopes. These subtle shifts were preserved when sediments hardened into stone. By examining these ratios, scientists can infer biological activity even when no physical structures remain. Carbon isotopes, in particular, offer valuable clues. Living systems tend to favor lighter forms of carbon during chemical reactions. As a result, organic matter and the rocks influenced by it often contain distinctive isotopic patterns. These patterns persist for billions of years, providing a quiet but reliable signal of life's presence. Iron-rich sedimentary layers also tell part of the story. As oxygen produced by early photosynthetic microbes reacted with dissolved iron, it caused iron minerals to precipitate and settle onto the seafloor. Over time, these deposits formed extensive iron-rich rock layers, Though shaped by chemistry, their existence reflects biological activity unfolding slowly across ancient oceans. The process of fossilization itself was gradual and selective. Most organic material was recycled, broken down, or dispersed long before it could be preserved. Only under specific conditions did traces remain. Calm waters, steady sedimentation, and low oxygen levels favored preservation by limiting decay. These conditions were common in early oceans, increasing the likelihood that subtle traces would endure. Sediments accumulating on the seafloor acted as protective blankets. As layers built up, they sealed older material beneath them, isolating it from further chemical alteration. Over time, pressure and mineralization transformed these sediments into rock, locking in the patterns formed by ancient life. Importantly, the fossil record from this era is incomplete and uneven. This patchiness reflects the nature of early life and the environments in which it existed. Life was widespread, but preservation depended on local conditions rather than global abundance. The absence of obvious fossils for long intervals does not indicate absence of life. Instead, it highlights how subtle early life was and how delicate the conditions for preservation can be. For much of Earth's history, life's record is written in chemistry rather than shape. Over time, as life influenced ocean chemistry more strongly, the fossil record became slightly clearer. Increased oxygen levels altered mineral formation, changing how sediments captured biological signals. Yet even then, the record remained quiet, requiring careful interpretation to reveal its meaning. These ancient rocks serve as bridges across time. They connect the present to a world billions of years removed, offering glimpses into processes that unfolded long before complex life appeared. Each preserved layer represents countless generations of microbes, living and dying in oceans that no longer exist. The study of these fossils reveals not only when life existed, but how it lived. Chemical signatures indicate metabolic pathways, environmental conditions, and energy sources. Through stone and sediment, it becomes possible to reconstruct aspects of early ecosystems. Even though no organism remains intact, there is a calm symmetry in this preservation. The same slow processes that allowed life to emerge also allowed its traces to endure. Sedimentation, mineralization, and time worked together to carry information forward. Nothing was hurried, and nothing was wasted. The fossil traces of early life remind us that history does not always announce itself boldly. Sometimes it whispers through layers of rock, requiring patience to be heard. Life's earliest successes were modest and easily overlooked, yet they laid foundations that would support all future complexity. As Earth continued its long evolution, these ancient records remained buried, waiting to be revealed. They endured through continental shifts, mountain building, and erosion. Only much later would they surface again, offering insights into the planet's distant past. In stone and sediment, the oceans of early Earth preserved their memory. Microbial life, though invisible to the eye, left an imprint that time could not erase. These traces confirm that life did not merely appear and vanish, but persisted, shaped its environment, and became part of Earth's enduring structure. By studying these quiet records, we gain perspective on the patience of nature. Life did not rush toward complexity. It lingered, repeated, and refined, and in doing so, it left behind a story written slowly, layer by layer, beneath the ancient seas. 18. The living ocean as Earth's first cradle. By the time life had established a steady presence in Earth's ancient seas, the oceans had become more than a setting. They were no longer merely collections of water shaped by geology and chemistry. They had become living systems themselves, woven together by energy flow, chemical cycling, and biological activity. In this role, the oceans served as Earth's first cradle, gently supporting life through its earliest and most fragile stages. From the beginning, water had offered protection. It buffered temperature extremes, softened chemical shocks, and shielded delicate molecules from intense radiation. As life emerged, these same qualities allowed it to persist. The oceans absorbed fluctuations that might otherwise have extinguished early organisms. In doing so, they provided continuity, ensuring that life did not need to withstand the full force of planetary change all at once. The oceans were vast, and their scale mattered. Their immense volume diluted toxins, dispersed waste products, and distributed nutrients across wide regions. Even as microbes altered their surroundings, the oceans integrated these changes slowly. This capacity for moderation allowed life and environment to co-evolve without destabilizing one another. The cradle did not constrain life tightly. It held it loosely, allowing room to adjust. Energy flowed through the oceans in many forms. Sunlight warmed surface waters and powered photosynthesis. Heat from Earth's interior rose through the seafloor, creating chemical and thermal gradients. Currents carried energy and matter across great distances. Life learned to tap into these flows, aligning its processes with the rhythms of the sea rather than resisting them. Chemical diversity within the oceans was another essential feature of this cradle. Dissolved minerals, gases, and organic compounds created a rich environment where multiple metabolic strategies could coexist. Life did not rely on a single pathway or resource. Instead, it explored many, adapting to local conditions and making use of what was available. This flexibility increased resilience, allowing life to persist across changing environments. The oceans also provided structure without rigidity. Depth, light, temperature, and chemistry varied gradually, creating layered habitats. Surface waters differed from the depths, shallow regions from open seas, sediments from the water above. Each layer offered distinct conditions, encouraging specialization while maintaining connection. Life spread not by conquering new realms, but by settling into niches gently carved by the environment. Movement was constant but unhurried. Currents mixed waters slowly, ensuring that nutrients and organisms could travel without being swept away too quickly. This circulation connected distant regions, allowing life to expand its reach while maintaining stability. Even isolated communities were never truly cut off, as water linked them across the globe. The oceans also preserved memory. Chemical signatures of biological activity lingered in water and sediment, influencing future conditions. Elements cycled through living and non-living systems, carrying the imprint of past processes. In this way, the oceans retained a history of life's interactions, shaping what came next through accumulated change rather than sudden shifts. Life, in turn, began to shape the oceans more profoundly. Microbial activity altered chemical balances, influenced sediment formation, and contributed to long-term changes in atmosphere and climate. Yet this influence remained measured. The oceans absorbed biological effects gradually, integrating them into existing cycles. The cradle supported life while also being reshaped by it. Importantly, the oceans offered time. In the seas, change unfolded more slowly. Temperature shifts, chemical adjustments, and environmental transitions were moderated by water's capacity to absorb and release energy. This slow pace allowed life to adapt through gradual variation rather than sudden crisis. The relationship between life and ocean was reciprocal. Life depended on the ocean for stability and resources, while the ocean increasingly reflected the presence of life in its chemistry and structure. This mutual influence did not require complexity or intention. For much of Earth's history, life existed nowhere else. The land was barren, exposed to harsh radiation and extreme conditions. The oceans alone provided the consistency needed for life to emerge and endure. In this sense, all later life traces its origins back to this watery cradle, shaped by conditions that favored patience and persistence. Even as oxygen began to alter the seas, the ocean's role as a cradle did not end. Anaerobic and oxygen-producing organisms coexisted, layered within the water column. The cradle expanded its capacity, supporting increasing complexity without losing its stabilizing function. The quiet success of the oceans lies in their balance. They were dynamic yet steady, diverse yet integrated. They allowed experimentation without chaos, change without collapse. These qualities made them ideal incubators for life's earliest stages. In reflecting on this period, it becomes clear that life did not struggle against the ocean. It flowed with it. The rhythms of tides, currents, and cycles became the rhythms of biology itself. Life learned to exist in harmony with its surroundings, guided by the same forces that shaped the planet. The cradle metaphor is fitting not because the oceans were gentle in a sentimental sense, but because they provided support without control. They did not direct life's development, but they allowed it. They offered conditions in which fragile systems could persist long enough to become resilient. As Earth moved forward, life would eventually venture beyond the seas, adapting to land and air. Yet the foundational patterns established in the oceans would remain. Cellular organization, metabolic pathways, and chemical strategies all carried the imprint of their marine origins. In the ancient oceans, life found a home before it found complexity. The seas held it through its earliest experiments, absorbing failures and nurturing successes alike. In this long, quiet embrace, Earth became a living planet, not through sudden transformation, but through sustained and patient support. The oceans, in their vast calm, were the first place where life could simply continue. And in that continuation, they fulfilled their role as Earth's first cradle, carrying life forward into a future still unfolding. 19. From early seas to a living planet. As Earth's ancient oceans continued their slow, patient evolution, the cumulative effects of life became increasingly difficult to separate from the planet itself. What had begun as isolated chemical processes and microscopic organisms now formed an interconnected system, spanning sea, sky, and stone. The transition from early seas to a living planet did not occur through a single event, but through countless small adjustments layered upon one another across deep time. The oceans remained central to this transformation. They continued to regulate temperature, distribute energy, and cycle materials, but now they did so in partnership with life. Biological activity had become a permanent feature of ocean chemistry. Elements no longer moved solely through geological pathways. They passed repeatedly through living systems, acquiring new roles and new rhythms. Carbon, sulfur, iron, and nitrogen circulated through organisms and environments alike, linking biology to the planet's physical framework. Photosynthesis, though still limited in scope compared to later eras, cyanobacteria and other light-harvesting microbes continued to capture sunlight, converting it into chemical energy and organic matter. The oxygen they released gradually accumulated, altering both oceanic and atmospheric chemistry. This change unfolded slowly, but its implications were far-reaching. Earth's surface environments were beginning to diversify in ways not previously possible. As oxygen persisted longer in surface waters, new chemical reactions became common. Compounds that were stable in oxygen-free conditions now transformed readily. Minerals changed form, and previously abundant substances declined. Life adapted to these shifts, finding new niches or retreating to environments that preserved earlier conditions. The oceans became layered not just physically, but biologically. The atmosphere also began to reflect these changes. Though still dominated by nitrogen and carbon dioxide, trace amounts of oxygen appeared more regularly. Over time, interactions between oxygen and sunlight contributed to the formation of an ozone layer high above the surface. This layer, though still developing, reduced the intensity of harmful radiation reaching the planet. For the first time, Earth began to offer protection beyond the seas. This gradual shielding opened possibilities that had previously been unavailable. The planet was preparing itself, quietly and without urgency, for future expansions of life into new realms. Geological processes continued alongside biological ones, maintaining a balance between change and stability. Plate tectonics reshaped continents and seafloors, altering ocean circulation and creating new environments. Volcanic activity introduced fresh materials into the system, while erosion delivered minerals from emerging landmasses into the seas. Life responded to these changes by adjusting its distribution and strategies, reinforcing the interconnected nature of Earth's systems. The notion of a living planet does not imply uniformity or harmony in a simple sense. Instead, it reflects the emergence of feedback loops that linked life and environment. Biological activity influenced chemistry, which in turn affected climate and geology. These changes then shaped the conditions under which life persisted. Over time, this mutual influence created a planet that could regulate itself within certain bounds, maintaining conditions suitable for life's continuation. Importantly, this regulation was not conscious or directed. It emerged from countless interactions governed by physical laws. Life did not control the planet, it participated in it. The balance achieved was dynamic, capable of adjusting to disturbances without collapsing entirely. The oceans continued to serve as the backbone of this living system. Even as life's influence spread, the seas remained vast and moderating. They absorbed excess heat, buffered chemical changes, and provided continuity across transitions. Their role as Earth's stabilizing force ensured that biological innovation did not outpace environmental capacity. As time passed, biological diversity increased slowly. New metabolic pathways emerged, allowing organisms to exploit different energy sources and chemical environments. Some microbes adapted to tolerate oxygen, while others specialized in oxygen-free niches. This diversification did not lead to immediate complexity, but it expanded the range of possibilities available to life. The fossil record from this period reflects this gradual transformation. Chemical signatures in sediments reveal changing balances of elements, while structural features hint at evolving microbial communities. Though still subtle, these records show that life was becoming a defining component of Earth's history rather than a fleeting phenomenon. The transition from early seas to a living planet was therefore not a moment, but a state. Earth crossed a threshold where life and environment became inseparable, each shaping the other continuously. From this point forward, planetary evolution could no longer be understood without considering biology as a central factor. This integration had profound implications for the future. With energy flowing through biological systems and oxygen altering chemistry, new forms of life would eventually become possible. Complex cells, multicellular organisms, and ecosystems would arise much later, built upon foundations established during this quiet era. Yet even as the stage was set for future complexity, the planet remained dominated by microbial life. Simplicity continued to define Earth's biosphere, not as a limitation, but as a stable and effective way of existing. Life had learned how to persist across changing conditions, ensuring its continuity through patience rather than speed. In reflecting on this transition, it becomes clear that Earth did not become a living planet by chance alone. It did so through a convergence of conditions sustained over immense periods. Water, energy, chemistry, and time aligned in a way that allowed life not only to emerge, but to endure. The early seas were the foundation, but the living planet was the result. Through slow accumulation of change, Earth transformed from a world capable of hosting life into one shaped by it. This transformation was quiet, measured, and deeply integrated, unfolding without drama yet with lasting consequence. As the planet moved forward, the influence of life would continue to grow, eventually extending beyond the oceans and reshaping the surface entirely. But at this stage, the essential connection had already been formed. Earth and life were now partners in an ongoing process, bound together by shared history and continuous interaction. From the ancient seas emerged not just organisms, but a new planetary state. Earth had become alive in a fundamental sense, carrying life within its cycles and structures. And with that transformation complete, the long journey toward greater complexity could continue, guided by the same patience that had shaped the planet from the beginning. 20. A gentle closing. Life begins and continues. As Earth's long story unfolds, the early oceans remain at its quiet heart. From cooling rock and falling rain to chemistry, boundaries, and the first organisms, there was no single moment when the planet became alive, no sudden transformation that divided before from after. Instead, life emerged as a continuation, a gentle extension of processes already in motion. The ancient seas carried this continuity with remarkable steadiness. They gathered water, energy, and matter, holding them together long enough for complexity to arise. In their depths and shallows, life found stability before it found variety, persistence before expansion. The oceans did not demand speed or novelty. They rewarded endurance, balance, and quiet repetition. What began as simple chemistry gradually learned how to sustain itself. Molecules assembled, separated, and assembled again, guided by energy and time. Boundaries formed not to isolate, but to protect and maintain. Reactions linked together, not with intention, but with consistency. From these patterns, life slowly took shape, indistinguishable at first from the chemistry that surrounded it. The first organisms did not alter the planet overnight. They lived modestly, processing energy and materials at a pace that matched their environment. For hundreds of millions of years, life remained microscopic, aquatic, and largely invisible. Yet its influence accumulated, molecule by molecule, layer by layer, shaping oceans, sediments, and atmosphere alike. Oxygen, once absent and unwelcome, began its gradual rise as a byproduct of light-harvesting microbes. The oceans absorbed its presence patiently, allowing chemical systems to adjust without collapse. Anaerobic life persisted, photosynthetic life expanded, and Earth learned how to host multiple ways of living at once. Change did not erase what came before, it layered upon it. Throughout this immense span of time, the rhythm of life remained slow. There were no forests or animals, no rapid bursts of diversification. Instead, there was continuity. Cells divided, chemistry flowed, currents moved. The planet breathed in long cycles measured not in years, but in geological ages. Life did not rush toward complexity. It waited until conditions allowed it naturally. The fossil record from this era reflects that patience. Traces of life appear as faint patterns in stone, subtle shifts in chemistry, layered sediments shaped by microbial activity. These records do not tell a dramatic story, but a steady one. They remind us that most of life's history unfolded quietly, without spectacle, yet with profound consequence. The oceans, as Earth's first cradle, carried life through its most fragile stages. They buffered extremes, softened transitions, and provided time. In doing so, they allowed life to become resilient before becoming complex. Every cell that would one day inhabit land, air, or deeper seas traces its lineage back to this watery beginning. As the planet continued to evolve, life and environment became inseparable. Chemistry influenced biology, biology reshaped chemistry, and together they formed a living system capable of adaptation and persistence. Earth did not become alive in opposition to its physical laws, but in harmony with them. Life followed the paths that energy and matter made available. Even now, the echoes of these early oceans remain within living cells. Metabolic pathways, molecular structures, and chemical preferences reflect conditions billions of years old. The patience learned in the ancient seas is still present, carried forward through countless generations. Life remembers where it began, not through memory, but through structure. In the calm perspective of deep time, the emergence of life appears inevitable only because the planet allowed it to unfold gently. Remove time, water, or stability, and the story changes. It was the combination of all three, sustained over immense durations, that made life possible. The oceans did not create life by force. They allowed it by presence. As this journey comes to rest, it is worth lingering on that idea. Life did not arrive fully formed. It assembled itself slowly, quietly, without urgency. It learned how to exist before learning how to change. And in doing so, it established a foundation strong enough to support everything that followed. The early oceans no longer exist in their original form. Yet their legacy is everywhere, in every cell, every breath, every living system. The imprint of that ancient world remains. Life continues because it once learned how to persist in water, guided by chemistry and time. And so, as this story settles into stillness, it does not truly end. Life continues, just as it always has, carried forward by the same gentle processes that shaped its beginning. The planet turns, the oceans move, and beneath it all, the quiet continuity of life endures, patient and unbroken, as it has for billions of years.